Good afternoon. My name is Jean-Louis Briot. I'm a distinguished professor in the Zachary Department of Civil Engineering and holder of the Buchanan Chair at Texas A&M University. Welcome to the 25th Buchanan Lecture. Time sure flies. This year's lecture is again sponsored by a generous gift from Fugro. Recep Yilmaz is here, and where's Recep? And Matt, the new CEO, is here. Sue Barrell, thank you all for coming. We appreciate your sizable support, and thanks to you, the Buchanan Lecture remains free of charge to all participants. I also want to recognize those who've sponsored graduate fellowship in geotechnical engineering, Terracon with George Cozart and the Terracon Fellowship, Alan Young, who created the Don Murph Fellowship, Willie Bowman and his wife Milfred, the Bowman Fellowship. We'd like to raise more funds for fellowship to support our geotechnical graduate students. We have a lot of fellowships for undergraduate students, but not so much for graduate students. As you know, the Buchanan Chair and the Buchanan Lecture would not have been possible without without Darrell Hooper, who started this whole process a long time ago, early 80s, right after Spencer Buchanan died. Darrell was a student of Spencer Buchanan and had the idea to recognize his professor by contributing to a chair for him. After his major gift, he turned to his classmates of the time and challenged them to contribute as well. Many stepped up and helped out. Doug Flatt stands out among those and continues to help us every year. Others include Don Avilés, Philip Buchanan, son of Spencer Buchanan, and many others. I cannot name everybody, but I can assure you that I deeply appreciate all the support you give to our program. I also want to recognize the students at both TAMU, UT, and other universities. Can the students stand up? I think we have an amazing crowd of students. Thank you all. I want to recognize, of course, our invited speakers, both Jonathan Bray and Tom O'Rourke. You'll hear a lot more about them in a minute. My colleagues in geotechnical engineering, Chuck Albany, Marcelo Sanchez, Zenon Medina, and Minsu Cha. On a sad note, Harry Coyle died this year. He's the man who hired me some 39 years ago and gave me a chance at this wonderful university. He was a student of Lyman Rees, who departed before him. Harry was my mentor and one of the nicest persons in the world. Let's observe a moment of silence in Professor Coyle's memory. Now the program. Dr. Jim Kaihatu, who is Associate Department Head, will say a few words about our department in a minute. He's substituting for Dr. Robin Ottenreith, who's on travel. Then I'll introduce Professor O'Rourke, who will then deliver the 2016 Terzaghi Lecture. Then I'll introduce Professor Bray, who will deliver the 2017 Buchanan Lecture. Then we'll take a photo on stage, as we've done for several years. And then we'll end the afternoon with a reception at my house. Maps on how to get there are at the front desk. Please sign the guest book. Where's the guest book? Anybody has the guest book? Thank you, Melanie. So please sign the guest book, which is circulating. Name and email is what we need from you. This is how we build our mailing list to tell you about next year's lecture. This is particularly important for the students in my class, as I give 5 points on the final for attending the Buchanan lecture. On the final, not on the final grade. The best way to find out about next year's lecture is to go to the Buchanan lecture website around September each year. We always host the lecture about the latter part of the fall. I also want to recognize Melanie Rodriguez. Melanie, my assistant, who's been working long hours to help me organize this lecture. Now I would like to call on Dr. Jim Kaihatu, Associate Head of the Zachary Department of Civil Engineering, to say a few words about our department.
Howdy, everybody. Thank you, Jean-Louis, for that introduction. As you mentioned, my name is Jim Kaihatu. I'm an associate professor in the Department of Civil Engineering. I'm also by research emphasis a coastal engineer, but I have worked a lot with those in the geotechnical community, so I am familiar with what you all do and appreciative. So welcome to Aggieland, welcome to Texas A&M, and welcome to the Terzaghi and Buchanan lectures. So what I'd like to do is offer a few brief remarks about the department, just basically where we are and where we hope to go. We're presently celebrating 130 years as a department of civil engineering in the University in Texas A&M University. In terms of our statistics, we are presently ranked number 8 in both undergraduate and graduate programs among all civil engineering programs in public universities in the U.S. I imagine we're probably number 1 in terms of universities with an ampersand in the title, but I can't be 100% sure. So, but anyway, that's as of the U.S. News and World Report from the one coming up. As of fall 2017, we have graduated over. We have over 700 undergraduates from sophomore to seniors. The college handles are freshmen, and they apply to become civil engineers. One thing I will say is that I'm also part of the selection process through a process we call entry to a major. We get way more applications for our department for students than we have seats for them. So that's really a testament to our stature and our perception among undergraduates. We have over 250 Master of Science and Master of Engineering students and about 166 Ph.D. students. So we are doing more than our share of supplying both academia, research industry, and industry with the next generation of civil engineers. As of last year, we graduated, conferred 220 bachelor's degrees, 113 graduate degrees, 12 of which were Ph.D.s. So that's very good statistics. In terms of our faculty, we have 55 faculty right now, 10 of which are assistant professors and 6 of whom were hired over the last 2 years. And these are faculty who have strong interest in interdisciplinary work, reaching out to other universities, other departments in our university, and also other departments in our college to expand and increase the impact of their work on the community. In terms of our research areas, we have many different research areas that our faculty work in. I won't talk about all of them, but I'll talk about some of the highlights. There's a lot of folks working in transportation dynamics. That is basically taking the computing and sensing power that are present in our modern-day automobiles and using them to improve traffic flow, to improve safety, to actually communicate with other vehicles and improve inter-vehicle communication in means that are more than simply angry gestures between drivers. Also, autonomous vehicles, making them more safe, more reliable, more trustworthy by those who might use them. Alternative fuel sources in terms of hydrocarbon extraction. Also looking at using recycled materials in asphalt and pavement for improving the sustainability. Waste remediation, particularly with respect to nuclear material storage. That's become more of an issue now that we're trying to move away slowly from fossil fuels, and nuclear is becoming a larger part of that profile now. Contaminant mobility. We saw during Deepwater Horizon, Hurricane Harvey, and other natural disasters that have occurred. The big flooding in Louisiana a couple years ago, for example, that have emphasized our need to be able to get a handle on the mobility of contaminants in the surface water, the groundwater, and the ocean. Right? So we're also working on improving our resilient and in the area of resilient and sustainable infrastructure. The Center for Infrastructural Renewal, which is being built on the Rellis campus in Riverside, is going to greatly expand our ability to do that by working in both working in things like sustainable materials and also doing some innovative testing. Also, we're working on the hazard side as well, being able to characterize the hazard, tsunamis, hurricanes, earthquakes, and seeing how those impact our designs, as well as risk assessment, trying to figure out if you're in an area over here, what's the risk of environmental hazard occurring, or an economic hazard, or even a societal risk, those sorts of things. So it's a way of coalescing everything we do into a picture that someone can use to do planning, to do civil defense, and making a very direct impact of our work on the community. Our department is interdisciplinary. We're trying to improve that. That's part of my job as Assistant Department Head of Research. We have several faculty who have joint appointments in other colleges and other departments, so that's really an indication that we're really trying to reach out and trying to improve our impact on the community of our work. We are increasing our offerings. We are actually going to begin an environmental engineering degree, all approvals pending, for fall 2019. So at that time, provided everything goes through, and we think it will, we will be able to offer an environmental engineering undergraduate degree within the civil engineering department, which is really something we're excited about. We've also undergone a great curriculum design, basically taking the input from folks like yourself, peer institutions, our industry, former students, trying to figure out what does the ideal graduate look like when they graduate from our program. How can they have the most impact in their community, and then work our way backwards through the curriculum and trying to figure out what do we need to change in order for that to happen. So that kind of work is getting us some national recognition, and we're really excited about it at this point. Right now, we're at the point of implementing all this into our coursework. So anyway, so I just wanted to offer a few words as to our department. I'm sure Dr. Rottenreith would have been really happy to be here. Unfortunately, she's out of town and asked me to step in. So, these are exciting times for our department. I hope you follow along, like us on Facebook, or follow us on Twitter, or I don't know what you do on Instagram, maybe stalk us or something. But we would really be happy to have you come along on our ride as we move forward into the future. So on that note, I'll close. I wish you, I hope you enjoy your time in Aggie Land, and that you enjoy the lectures, and safe travels back home. Thank you very much.
It's now my pleasure to introduce to you Professor O'Rourke. Tom O'Rourke is the Thomas Briggs Professor of Engineering in the School of Civil and Environmental Engineering at Cornell University. He's a member of the U.S. National Academy of Engineering, distinguished member of ASCE, International Fellow of the Royal Academy of Engineering, member of the Mexican Academy of Engineering, and a Fellow of the American Association for the Advancement of Science. He received a number of distinctions for his research and teaching, including the Stephen Bechtel Pipeline Engineering and Ralph B. Peck Awards from ASCE. He gave the 2009 Rankin and the 2016 Terzaghi Lectures. He served as president of the Earthquake Engineering Research Institute and as the chair or member of many professional society committees. He received the George Husner Medal from EERI in 2016. He authored or co-authored over 380 technical publications. His research interests cover geotechnical engineering, earthquake engineering, underground construction, engineering for large geographically distributed systems, and geographic information technologies and database management. He served as an advisor on more than 120 projects in 13 different countries. He testified before the U.S. House of Representatives Science Committee on numerous occasions. He served on government advisory boards as well as the consulting boards or peer reviews for many projects associated with highway rapid transits, water supply, and energy distribution system. Most impressive biodata. The title of his Terzaghi lecture is Ground Deformation Effects on Subsurface Pipelines and Infrastructure. Please welcome the 2016 Terzaghi lecturer, Professor Thomas O'Rourke.
Thank you, Jean-Louis, for the nice introduction, and welcome, everybody. It's really nice to see such a great turnout, and I'm very pleased to be here. I also would like to congratulate Jean-Louis, faculty, students at Texas A&M for having the Buchanan lecture, inviting the Terzaghi lecturer, and just throwing a great show. Thanks a lot. You've contributed quite a bit to the geotechnical profession, and this is a manifestation of all that good work. Thank you. It's well known by some that Terzaghi had a dueling scar, which he received while dueling at some arcane Austrian dueling society. And in recognition of Terzaghi's dueling scar, I thought I would come sort of, how can I put it, facially appropriately administered for this particular talk, so that I could recognize Terzaghi and his idiosyncrasies. Today I'm going to talk about ground deformation effects on subsurface pipelines and infrastructure, and I'd like to start by recognizing some of my colleagues and students at Cornell. These are the people that really did the work, and I'm just the spokesperson. So they deserve the credit for what I'm going to say, and I hope I do them justice by saying it well. I also like to recognize the National Science Foundation, who supported, or which supported, many, many years of research at Cornell and lots of other places, doing a lot of good for a lot of people. They certainly deserve the recognition for the support they give us, and especially that they give geotechnical engineering. This is a picture of the Trans-Alaska Pipeline where it crosses the Denali Fault. It's above ground. It was subjected to fault rupture along the Denali Fault during the 2002 Denali Fault earthquake, where the fault at this location moved 18 feet right laterally and 2 feet vertically. And of course, that pipeline was able to accommodate the deformation because of the prescience on the part of the engineers who could identify where the fault was and recognize that they needed to take it out of the ground and put it on special skids. But when we deal with the thousands and thousands of kilometers of pipeline that we experience and that we work with to support our modern infrastructure, aren't able to take all the pipelines out of the ground, and therefore we have to deal with the effects of large ground deformations, especially during extreme events, but also during construction, dewatering, subsidence, and a variety of other things which cause large ground deformations to affect these facilities. The topics I'm going to cover today are as follows: our underground assets, soil pipe interface, soil pipeline interaction, 2 and 3D behavior, next generation of pipelines, and then pipeline system performance and impact on communities. Let's start with the underground assets. This is a quick slide with the inventory of pipelines that operate in the United States. As you can see, there's almost 500,000 kilometers of gas and liquid fuel transmission pipelines. There are about 2 million kilometers of gas distribution and water distribution pipelines. A recent report by the American Water Works Association places a value on the water distribution pipelines of about $2.4 trillion in place. Since we have similar distances of water relative to gas, we're actually looking just between gas and water distribution at nearly $5 trillion of investment in the ground. That's enormous, and it's very difficult for you to walk anywhere. In fact, probably just in this building with internal piping, you're sitting on a pipe right now. But the minute you walk out of this building and go across the street, you probably cover at least 6 of them. They're ubiquitous. They're all over. We take them for granted. They're the national treasure, and like every treasure, we bury them. And then we don't know where they are. We don't know what they're doing, and we have to try to come up with evaluations and ways to engineer with them. Let's take a quick look at the U.S. pipeline inventory, because this is going to factor into what I have to say today in terms of an overall philosophy. If we look at the water distribution pipelines by size, we'll see that there is about 90 to 95% which are less than or equal to about 24 inches in diameter, 600 millimeters in diameter. If we look at gas distribution systems, using the statistics that from the Pipeline and Hazards PHMSA group in Washington, about 99% of the gas distribution pipelines. So the great majority of these things are about 2 feet or less in terms of diameter. And then, of course, we have a lot of transmission lines that go higher than 2 feet. If you're working with water in Southern California, Metropolitan Water District operates pipelines on a frequent basis of 4 to 5 meters in diameter. They're sort of mini tunnels. We don't have to wait for an earthquake to have a disaster in pipelines. This is a newsreel from Korean television, and watch the explosions that are occurring here. This actually, now, by the way, this is South Korea, not North Korea. And you can see that there is a kind of a subtext going on here called revenge of the infrastructure. They were trying to determine where there were going to be failures in their lines. They decided to start to pressure test them with nitrogen. Unfortunately, that's highly compressible. And when you do find a flaw in the pipeline, it expands rapidly and caused explosions. It actually triggered a very significant research endeavor on the part of South Korea to look into their underground assets. Today's talk is going to be focused on extreme soil pipeline interaction, the kinds that are created by earthquakes, particularly ground failures, generated by earthquakes, hurricanes, floods, landslides, both aerial and submarine, tunneling and deep excavations when movements become large, and subsidence of all types, removing petrochemical gas deposits, or if you happen to be in the areas of California or Phoenix, where lots of groundwater has been extracted, you'll find that there are large faults, normal faults, associated with these subsidence basins at the margins. The issue about extreme soil pipeline interaction are the nonlinearities. There's the material nonlinearities, for which I think the geotechnical profession, civil engineers, have a pretty good grasp. We can actually account for nonlinear behavior of complex materials, starting with the soil, going with the pipes, going with the perhaps polymers, going with the linings. They become much more complicated when we start talking about composite systems with all sorts of layered materials. But we can handle that. The issue really, in terms of modeling these things, is the geometric nonlinearities. This is a picture of some measurements and observations that we took during some of the large-scale testing at Cornell. And as the soil fails and develops its maximum interaction force with the pipeline, it's no longer the soil it started as. And it's no longer the soil it started as for really important reasons. That means it's been transformed geometrically. We get strain localization, we get tension cracks, we get voids. Things alter, and it's very, very difficult to model the geometric nonlinearities. Even the pipelines. This is a picture of one of the major trunk lines that went into San Fernando Valley and was damaged during the San Fernando earthquake in 1994. The Northridge earthquake in 1994. And you can see that this pipe is wanting to change geometrically too, but it just isn't able to do it with these welded slip joints. They ended up failing and cracking as they were trying to transform to accommodate the ground deformation. So the philosophy, and one of the things we're going to see, is that in developing the next generation hazard-resilient pipelines, we're creating pipelines that fight fire with fire. They fight the geometric nonlinearities of soil by transforming themselves in a geometrically nonlinear way, either by having special joints which can move in compression and tension axially, rotate large amounts of degrees without leaking, or have stretchable and bendable and ductile materials incorporated into them. So the way in which we are adjusting to permanent ground deformation effects to geometric nonlinearity is we're creating shape shifters. Next topic, soil pipe interface. These are some pictures at Cornell on our large-scale testing facility. So this is actually looking at a strike slip movement with no soil, so you get a sense for how the pipe is bending and stretching. This happens to be a 400 millimeter or 16-inch high-density polyethylene pipeline. And here's the soil in place, and you can see all this ground rupture and so forth, which is occurring around it. But where the rubber really meets the road is right here at this fault crossing, where we get, very high levels of lateral deformation, lateral pressure imposed on that pipeline. And as you bury it deeper or you move the fault more, that interaction grows and will eventually fail this very, very ductile pipeline that doesn't want to fail longitudinally or in bending. You'll eventually squeeze it shut if it doesn't have the appropriate pressure inside it. So this is where the rubber meets the road, and we tried to take a close look at some of this behavior by using tactile pressure sensors. Now these are resistive ink, sort of geotextiles if you want, sensor systems. This one that we were using on our 400 millimeter diameter pipeline was about 50 by 400 centimeters in plan, and it contained about 2,000 measuring units. And you get the voltage drops across of all those, and then with the voltage drops, you can relate that to local pressures, and then you have special visualization software. You can characterize the distribution of pressures along nonlinear surfaces. This happens to be a circular surface, and of course, it's along that circular surface that you generate friction. And friction, of course, causes the pipeline to differentially stretch or compress and develop strains. We tried to understand that by running a series of tests for plane strain movement of the pipe through the ground. So we had controlled deformation conditions. We could model that then as a two-dimensional soil structure interaction. And we also could use our tactile pressure sensors to understand what was happening at the pipe-soil interface. So what a tactile pressure sensor does is it measures the stress normal to the exterior surface of the pipe. But we can actually decompose the stresses that are on the pipe into their horizontal components. We're going to have a normal component. We're going to, at one location. We're going to have a tangential component. We can decompose both of those into their horizontal components, and we can integrate. And this is showing the integration in terms of closed form, and this is showing the integration in terms of numerics that would be tailored to the type of measurement that we're making in the tactile pressure sensors. And so we can come up with a horizontal force per unit distance that we can plug into a two-dimensional soil structure interaction model. This is showing the actual measurements from some of these tests with the tactile pressure sensors. And these are normal stresses to the surface, the ones that generate the friction. And we can take those normal stresses through many, many different measurements and many different tests. I think this is representing something like 27 or 28 separate sets of measurements, and regress these into a dimensionless pressure distribution where we have the normal stress at any angular distance normalized with respect to the maximum stress, and actually get a sort of sinusoidal characterization for that stress system. Just for interest, we actually took some of the plane strain two-dimensional soil structure or pipeline structure interaction model we did, and we actually looked at the normal stresses that was generated by those numerical models, and they actually followed very closely the distribution that we were getting in the tactile pressure sensors. So we can actually characterize the true longitudinal friction that's being generated along that pipe by horizontal movement into it. That has got to be a function of a three-dimensional transfer of stress. We've got the normal stress transferred around about 180 degrees of the pipe, because as the pipe moves through the ground, it tends to pull away from the soil behind it. And we can take that normal stress and multiply it by the tangent of delta, the angle of interface shear resistance. And then we can compare that to what I would call the apparent force, because when we do the numerics, when we break this down into two-dimensional soil structure interaction, we're actually looking at the horizontal force per unit distance. And that actually does not generate the true frictional force. However, we can, from our measurements here, take the true one, divide it by the apparent, and we have a conversion factor that will allow us to go from a two-dimensional characterization of force perpendicular to the longitudinal axis of the pipe in the simulations to a three-dimensional circular circumferential transfer of normal stress, then transferred into shear stress along the pipeline. And when we do that, we get these kinds of characteristics where we're plotting this ratio of the true relative to the apparent force per linear distance of pipe relative to the coefficient of friction, or the tangent of delta for the interface friction angle between the pipe and the soil. And we notice a couple of things. If we coat that pipe with, which we often do, a polyethylene or some form of fusion epoxy, we're getting a tangent of delta which is between about 0.4 and 0.5, and there's no correction that's necessary. However, if we have bare steel, which tends to get rough and develop some oxidation, or if we have a concrete pipe or a concrete covered pipe, often you find that in water distribution and water transmission, you have to make a correction here because you're over characterizing what that characteristic shear transfer is going to be. We went further. We actually looked at our sensor measurements, and then we looked at a number of numerical results, which I'm going to talk about in a few minutes, both for the lateral movement, the upward movement, the downward movement, did the same kind of characterization of true relative to apparent versus tangent of delta, and they all follow a very narrow range. And so this characterization works in all different directions insofar as we've been able to show, and we can characterize this with some sort of a curve like that that allows us to make the corrections from a two-dimensional into a three-dimensional enveloping friction transfer function. So what do? We then create a model in our finite element modeling. We use Abacus. It has a very nice library of different elements that we can make adjustments to. And we could put gap elements in here, which are going to be controlled by the Coulomb friction law. And when we do that, we then have a coupled horizontal force displacement relationship that generates a true representation of our longitudinal friction down the pipeline. So lessons from soil pipe interfaces, the relationship between soil, force normal to the pipe surface versus force normal to the pipe longitudinal axis. It's really a key, understanding that, for modeling coupled soil pipe interaction. And the evaluation of friction along the pipe from soil force normal to the longitudinal axis is a contribution that can be made through this lecture, and in it, really, we're going to see a little bit later, it really improves things. I find in practice a lot of people not appropriately accounting for the real horizontal forces that are being transferred to the pipe, which in the zone of fault rupture or ground deformation, which is the most severe, puts a very high normal stress on the surface of the pipe, thereby amplifying friction at that location and causing what we call strain attenuation. You get a very rapid attenuation of strain, which means you concentrate response in high levels of strain, which is what ends up breaking pipelines. Next topic, soil pipeline interaction. We, over the last 20 years, have tended to model soil and pipe by virtue of a kind of PZ and PY and TZ types of analyses that were developed by Lyman Rees and other people for piles. And this has worked very well. We have gone well beyond spring slider elements. I want to say that what we do now is we account for some very complex nonlinear force displacement reaction, which we have been able to characterize, and then we've been able to scale and project to other dimensions and other kinds of soils to look at this two-dimensional transfer between stresses in terms of movement and interaction with the pipeline in a pretty comprehensive way. So we can replicate complex interactions in the pipe and soil. We also notice that there's been tremendous three-dimensional modeling developments in the last 10 years. These are examples of some really significant papers that have made great advances in solid element modeling around pipelines. One of the very best is Vazouris et al., 2012. If you really want to read a great paper about three-dimensional modeling of pipe fault abrupt deformation interaction, that's a really good paper. But the challenges of trying to duplicate the complex three-dimensional geometric nonlinearities and also pipeline nonlinearities that go along with this process in 3 dimensions is a formidable challenge. Progress is being made, but we're going to have to wait a few years more for that to catch up, or at least catch up in a way which is relatively affordable and in a way that could be done relatively rapidly. So in the meantime, I'm going to concentrate on 3D and 2D, but I'm going to look at 2D number 1. And as I said, one of the kind of advances we can make is accounting appropriately for this coupled horizontal or vertical or transverse deformation in terms of the frictional resistance along the pipe. We also are able to characterize the nonlinear joint response if we're dealing with pipelines that are shapeshifters. So we can look at nonlinear axial joint slip versus displacement, moment versus rotation, shear versus transverse moment. We also have been able to most recently account for axial joint slip and progressive slip transfer to other joints. Some of the ways in which these pipelines accommodate large ground deformation is that they slip several inches axially, then they lock up, and then they have a resistance to that force. And as they deform more, that transfers the deformation to the next joint down the pipeline, and it slips and locks up. We can do this. We can do this with great accuracy now that actually duplicates these large dimensional tests and shows how the pipeline is opening up en echelon because it jumps back and forth across the fault as you're pulling this pipeline apart and getting the thing to slip. We can look at load drops across the bells and spigot joints, which in some of these special joints are very enlarged bells. They act as little anchors. And if you don't account for the stress that's dropped across those or the load, you'll come up with an underestimate of the axial force the pipe ultimately has to carry for a given level of deformation, and that will be unconservative. So there are some tremendous advances. Now, one of the things we like to recognize when we do our work at Cornell is this relationship in the direct simple shear test between plane strain and direct simple shear. We know that the plane of rupture in a direct simple shear test is a plane of zero extension. And recognizing that fact and the fact that you have coaxiality of strain and stress in terms of Moore circle characterization for the direct simple shear test, one can, on the basis of work that was done by Davis, the great Australian geotechnical theoretician, we can come up with a relationship between direct shear and plane strain. Well, this gets back to our plane strain tests. If we can use the characterization from a direct shear test, direct shear test, to actually be able to look at the plane strain strength characterization, which is performed using the angle of dilation here, so we get this out of the model at the same time, we actually can develop good plane strain models. We also recognize that the interface between the pipe and the adjacent soil is a surface of zero extension. So the best strength to characterize that surface is the direct shear test because that actually accounts for that stress transfer. So from one test, you can get a characterization. We look and work with glacial fluvial sands, and we have looked at densities from medium to very dense. These are the dry densities. These are the direct shear peak angles of shearing resistance. These are the plane strain ones. They're always higher. And these are our angles of dilatancy. Notice that we have focused on soils that are dilative. Contractive soils tend to collapse. They're very difficult to try to characterize. And our recommendation would be that if you're dealing with a contractive sand, which you typically don't want to do when you're backfilling a pipeline, but if you are, then just use the model for a medium dense. It'll give you a conservative but not overly conservative estimate of the interactions. So here's some of the tests that we performed, and then we developed our plane strain finite element analysis with a model that uses a more Coulomb yield surface that has strain compatible modulus in it and also a strain softening routine to go from peak to residual shear stress here. And here are some of the simulations for a particular depth to diameter pipe. And here's the thing frozen out like this. There's a void that's forming behind the pipe. And when we compare this test, which was for a partially saturated sand, with one that we actually ran, there's a pretty good characterization and similarity in the vectors and the geometry of the soil that's being mobilized to resist the pipe's movement horizontally. In fact, if we take our data and we compare it to our best large-scale field tests, or excuse me, laboratory tests, and we look at the dimensionless force relative to dimensionless displacement, and this is dimensionless force divided by the depth and the diameter and the unit weight of the soil relative to dimensionless displacement. In this case, it's the displacement, relative displacement between pipe and soil divided by the diameter. We really can achieve a remarkable degree of fidelity between our large-scale test results and the actual model that we chose to look at for those interactions. And we used the best of our tests for lateral and uplift forces. We're actually lifting the pipe up in the soil in a two-dimensional way. And what you see here are in the dark lines, the analytical or numerical results, and in the points, the actual experimental results. And we get extremely good agreement between what we're modeling in terms of our maximum dimensionless horizontal force relative to dimensional depth. In this case, it's the centerline depth of the pipe divided by the diameter of the pipe, both for the lateral force and uplift. So with that encouragement, what we can do is we can build off of that kind of validation and extend our plane strain two-dimensional finite element analysis to look at vertical downward and then look at all degrees of oblique displacement between the pipe and the adjacent soil. We have semi-infinite finite elements out here on the margins, and we go through systematically looking at these force displacement relationships in the various orientations. So here we've got dimensionless force divided by dimensionless depth. We can sort that out in terms of medium, dense, very dense sands. And then we also can compare the finite element force that we're getting from these characterizations with the actual calculated tip resistance from bearing capacity formulations. And interestingly enough, we find that our results are only giving us bearing forces of about 1/2 to 1/3 conventional bearing capacity. We were concerned about that, so then we went back in and we analyzed the pipe as a bearing element that had a circular tip to it, and then ran these tests again and compared them with the actual conventional bearing capacity formulations, which should work for a shaft or a bearing element that goes down some height over the diameter. And we found excellent agreement between those. Looking further at why we have a difference here is the following. As the pipe is pushed down into the ground, the soil moves up and around and fills in the void behind the pipe. So it's not similar to pushing down a bearing element for which you're getting the bearing capacity relationship. And that one is far more constrained in terms of the theoretical model results relative to what's actually happening as a pipe is pushed forward. And in fact, there is experimental corroboration of these analytical work in terms of work that's been done at RPI, where they actually measured bearing forces which were about 1/3 to 1/5 of what was the theoretically predicted one. Well, this is pretty serious because we've been using conventional bearing capacity formulations for 20 years to evaluate these pipes. And we can see a way where we can improve that particular interaction. I have to tell you that this, strangely enough, I've searched the literature and called all sorts of people, including Dave White and people that are really involved in offshore, and no one's actually done the bearing capacity tests on the pipe yet. So this still requires some experimental confirmation. It should be an easy test to do. We're going to try to line ourselves up to do that. But if you want to beat us and put in a great NSF proposal, this is a good place to start. We're all about all sorts of people doing good work. So here we're looking at 45 degrees downward, upward, characterizing it again in terms of the different densities of the soil. And what we can do is, for various dimensionless depths, we can give you a three-dimensional view of what the horizontal resistances look like, because we can scale relative to our dimensionless horizontal forces, which we have great confidence in because we've tested them again and again and again, and have had lots of confirmation and lots of confidence that these are good. And so normalizing with respect to the horizontal, we can characterize the dimensionless maximum force in all orientations around the pipeline as a ratio of the two. And that applies for the medium sand, dense sand, and very dense sand in the same way. So in one set of diagrams here, we can characterize for all different orientations and depths of burial to have a complete force displacement representation for the pipe's interaction with the soil. As you can see, when the dimensionless depths are getting deep enough, it's symmetric. It's circular around it because the pipe's so deep it doesn't realize that it's shallower buried and you have less force going upward than downward and so forth. We can also, and I won't dwell on this, actually come up with an equation which characterizes these forces, which you'll see here. I'm not, as I say, I don't want to spend the time, but we actually can come up with an equation as well as a series of graphics and be able to characterize these maximum forces. We also have gone through and characterized the force displacement relationship. So once you know the maximum force, that sits the top here, we've used a rectangular hyperbolic formulation, very well known in geotechnical engineering, and also a bilinear one here. And you can, in some of our recent papers, you can actually specify what this force displacement relationship is for different obliquities of relative movement between pipe and the soil by picking these parameters A and B. So for example, if we happen to do that for the horizontal dimensionless forces and normalized displacements, these parameters A and B are 0.2 and 0.82, and we get this nice nonlinear characterization, or you can look at a bilinear characterization. The final piece of this thing is to recognize unsaturated soils. Generally, unsaturated soils are our friend. They're partially saturated. If you want to induce a shear on an unsaturated soil, like you're worried about slope stability, then it's got this suction that gets mobilized and it has enhanced strength. So if you ignore the effects of unsaturated soil conditions, you're generally safe because they're there giving you additional capacity that you're not really accounting for. But when you're pushing a pipe or you're pushing the ground against the pipe and you're ignoring suction forces, then you're getting a force which is just plain too small. And we need to characterize this. We worked with Kenichi Soga and his group in Cambridge, recent paper published in the Geotechnical Journal, to analytically evaluate this thing, run the tests, and then compare those against the large-scale tests at Cornell and large-scale tests on a different type of sand in an equally large testing facility at Tokyo Gas. So you have two different organizations running different types of sands through which this analytical comparison or numerical comparison is being made and therefore validated by two different labs at two different scales and two different types of soil. And we can summarize the results of those findings in these series of grain size distribution curves. So the boundaries on this happen to be for a Class 2 backfill specified by ASTM. And as you get smaller and smaller in grain size, so that your grain size distributions migrate to the right, you get larger and larger surface tensions, and therefore greater and greater suctions. And so what I did in this particular plot is to take the analytical results from that other paper and put it into this graphical form so you can divide the ASTM Class 2 backfill into zones of negligible suction effect, low, moderate, and high. Negligible, it behaves as if it's a dry sand. You really don't have to, because the grain sizes are so large, you just don't develop the kind of suction that's going to create any additional reaction force as the pipe and the soil are moving differentially with respect to each other. But over here, close to the silt line, you're going to get a very high potential, which could be as much or as 2 or 3 times the dry sand equivalent. So we have an adjustment here. And you can use this. The whole purpose of this is not to provide a hardcore analytical comparison, but to test. If I'm running a pipeline in a soil that I'm not accounting for suction in, and I look at its grain size characteristics, first of all, do I have a problem? If I do have a problem, if this stuff is finer grained, if I expect I'm going to have a horizontal, backfill it with the other stuff, all right? So you can select a backfill which will reduce that. Oftentimes, if you increase the wall thickness a little bit, you really improve the structural performance of the pipe. So this really is supposed to act as a check. If you actually find that there is an issue there, then you can start to bound the problem. If you can't solve it straight away, then you would need to take some more special measures to try to resolve it. So we end up with a design procedure where we specify these pipe and soil parameters, and we ask ourselves a question that given the dimensionless depth of burial, are there any pipe size effects? And if the answer is no, we go down to here and we say, based on the grain size distribution, is there any potential suction effects? If the answer is no, we're clear. If we stop up here and we say, yeah, there are pipe size effects. Because remember, our characterizations, and this happens to be for lateral and this happens to be for vertical downward, our characterizations are based on dimensionless depth. Well, you could have a pipe that has a diameter of 6 inches and its dimensionless depth at 4 is relatively small. And you could have a pipe that's 36 or 48 inches in diameter and its depth at a dimensionless depth of 4 is a lot deeper than that. And remember, our model accounts for dilatancy. So when you have lower confining stress, your dilatancy angle is much larger and you have a higher relative force, whereas you get deeper, the suppression of the dilatancy angle actually results in a lower force reaction. So, looking again at some of our test results, when we incorporate these findings and we look at our measurements relative to these true coupled reactions and characterizations, we find that we get extremely good comparison with both measurement and with the analysis procedures that we've been able to develop. I mean, a legitimate question really is, if I'm using force displacement relationships based on plane strain formulation, can that work for a pipeline that's being deformed? Sometimes they are deformed, and plane strain, like for a landslide, could be the dominant mode of deformation, but at other times, at a fault crossing, that's not necessarily going to be true. But characterizing it in terms of plane strain provides a consistent, rational basis so that our models and our test results are consistent. And when we use these formulations with the real three-dimensional deformation conditions, we do get good comparisons. They do go true. So our lessons in terms of soil pipeline interaction is we have an integrated methodology for soil pipe interaction. It's really for depths greater than or equal to 2. It turns out that at shallower depths, things get a little more complicated. We can't claim to cover those depths. But my comment is, if you're in this depth range, then just use a depth which is equal to 2 or slightly larger, and you'll get a very good approximation of it. Simulations show this vertical downward soil pipe reaction as being 1/2 to 1/3 the conventional, and then we have a way to characterize and account for the suction-enhanced soil pipe forces. Okay, so next topic is 2- and 3-dimensional behavior. I'm going to go relatively rapidly on this because I don't want to use up any more than my allocated time. As I've indicated to you before, we actually now can characterize this sinusoidal distribution of pressure around a pipe, and we can take frequently used diameter to thickness ratios. We can apply that force as a following force. Now, in reality, it's not a following force. It's going to be, there's going to be arching. So as this force starts to interact with the pipe and the pipe starts to deform a little bit, there's going to be arching and reduction of this force. So this is actually a conservative test. So we're looking at applying the force and seeing if this pipe ovals when we model it as a shell element, as a simply supported structure here with the actual approximation of the interaction force between the pipe and the soil. And when we run through these tests, applying that load, and get the results out over here, what you see is the diameter reduction in terms of percentage diametrical strain. And you can see at about 24, about 600 millimeters, 600 millimeters to maybe 750 millimeters, we have this rapid increase in out-of-plane deformation of the pipe. So what we see is for steel pipe and cast iron pipe, where we're following the stress state, this is a brittle failure, so if your stress gets too high, you're in trouble. what we see is that the pipeline begins to round out of plane, typically between 24 and 30 inches, so that our two-dimensional modeling actually can be quite accurate and quite true to the real behavior for 95 to 99% of all pipelines in practice. For the larger ones, which get into larger diameters, you may want to do a three-dimensional analysis, because when you start designing for a pipeline that's 60 inches, 5 feet, or 12 feet in diameter, this is a major special structure. If it's crossing a fault or in a ground rupture zone, you really do need to start to look at the out-of-round conditions and take a look at them more closely. So this is a picture of the Alameda Siphon number 2 crossing of the Calaveras Fault that was built by San Francisco Public Utilities, 1.7 meter diameter pipeline. You can see it, the scale of this thing relative to this person here. It's in this geosynthetic trench, so it actually slides up. They're actually trying to reduce the lateral pressures. But in this case, they had to make a decision. It turns out that if you want to model a pipeline as a shell, and you want to look at the out-of-plane deformation, even if you have a little pressure in there, like 100 psi, like a megapascal, it keeps it from ovaling, because that pressure relative to the soil pressure is about the same. It keeps it from rounding out. But if you drop your pressure below that kind of a threshold, it'll oval up very rapidly. And whether it has pressure in it or not is an operational decision. You can have a pipeline crossing a fault, and if there's no reason for the water pressure to be reduced in that pipeline, it's fortified against ovaling. But since that pipeline is connected to a pump station or to a reservoir or to something that can be damaged by the earthquake and lose its internal pressure, then you don't have pressure in it from an operational perspective, and it can just oval up shut. So there's a larger scale decision making that has to come in here. SFPC decided that they had to account for loss of pressure for a number of reasons I don't have time to get into. And then that required a wall thickness at about the greatest thickness that can be repetitively and quality welded. About an inch thick weld for a pipeline of that size is about as high as you can go in practice. Okay, so next generation hazardous resilience pipelines. Real quick in terms of historical development, this is Craig Davis. When he was the chief geotechnical engineer at Los Angeles Department of Water and Power, and he had gone to Japan a number of times, he asked U.S. pipeline manufacturers if they could build a pipe like Kubota pipe, which has been built and tested in many earthquakes. It's a ductile iron pipe. It has joints which will expand axially, will move in compression axially, will rotate a lot. It's a shapeshifter. It rotates and changes length. And they said no. And then he turned around and gave him a huge contract, and you know that generated so much innovation from pipeline manufacturers, because a little bit of competition goes a long way when you're talking about millions and millions of dollars with these water agencies in terms of orders of pipe. And so many people stepped forward with really innovative ideas. So far at Cornell, we have qualified these 5 types of shape-shifting pipelines. We're working on another 5 because IPEX has come back with an expanded bell. Now it not only stretches, but it moves in the bell. It can accommodate all sorts of deformation. And this is a cured-in-place pipe lining system over here, an aquapipe, which we hope to be testing next. And we test them in our large-scale testing facility. Here's a picture of some of the tests that are going on. We actually did the protective vault for the Bay Division pipelines 3 and 4 for San Francisco Public Utilities, where it crosses the Hayward Fault. This was a 1/10 scale model, so we could model how the various blocks were moving back and forth. And we came up second for an Opal Award on that. We were part of the design team, actually took it to 60% design. And there's a picture of a molecularly oriented polyvinyl chloride. That's where you expand the polyvinyl chloride while it's still hot in the fabrication process. You orient the molecular chain so that you enhance your tensile capacity. When you enhance your tensile capacity, you can sustain a pressure at a smaller wall thickness. And it's not so much the ductility of the polyvinyl chloride, but it's that reduced wall thickness that provides for that flexibility in a transverse direction. Look at this thing. You can actually bend it shut and it'll actually recover. But what is really amazing about this is when you take a pipe that can squash like this and push it. So this is the spigot side, this is the bell side. If I push this pipe into the bell, it actually sabers down. It actually multiple wrinkles and slips into the adjoining pipe because its wall thickness in the transverse direction allows for a longitudinal shortening, and the pipe can accommodate all sorts of compressive deformation. Nobody would have known that had you not done the testing. And here's a picture of it. Here we're pushing on it. See that pipe is going right past the bottom of the joint. I understand that the clamp or the restraint on there, which keeps the pipe from pulling apart, is not on this. We ran test after test with the clamp, which provides a lot more confinement, and it still happened again and again. So an amazing innovation. This is what I call the beer can mode of pipe collapse. And this is a type of pipe that's manufactured and been developed with these fuses. They start the buckling process, and once you start the buckling process, it keeps propagating and propagating and propagating. This is JFE. They're the old Nippon Steel, about 45,000 people worldwide. And this is an amazing piece of equipment. I'm always amazed. Here's what it looked like as it came out of our test. This one is designed for compression, because if you get into a compression zone, pipelines are thin-walled cylinders, and they don't like to be compressed. So these people have found a way to get it. So here's what happened after we subjected to the fault deformation. Here's what it looked like before. Here are these wave features that start the buckling process. So you can see this started out this long. It's now a lot less long in the longitudinal direction. And because it starts to rotate, because there's an oblique fault movement on this thing, as it starts to rotate, it actually absorbs more axial compression as well as rotation. And this is what the pipeline looked inside. It still maintained 80 to 85% of its throughput after excessive compression deformation. Other things we've been able to do is look at these enlarged bells. So the pipelines that actually allow for this axial movement back and forth. This is a Kubota pipe. This is a U.S. pipe that's been manufactured similar to Kubota, their own special design. And if you account for the load that's dropped across these bells, we're showing here our comparison of our analytical models with the actual large-scale tests, we get really good comparisons. We are dropping about 5 to 7 kips across each of these bells. If you don't account for that in the modeling of the pipe, you're going to be under-conservative for sure. And all our results from all the different companies are put immediately up on this website. And anybody can go there, take down our reports, read it, have access to it. It's open for everyone, because if you're going to do something in this kind of context, it needs to be transparent. Everybody should have access. So, lessons learned from next generation hazard resilient pipelines. This is a paradigm shift in pipeline technology, building pipelines that are shapeshifters. It's a market-driven research model. We don't receive a penny from NSF or the federal government or anybody else. This is all coming from private industry, and we're as busy as we can be. You can't have resilience unless you have a market. If only one company is providing you with a shape-shifting pipe, they can charge whatever the market will bear. But if you have competition, you have a market. You actually can get a better price, but what's more important, you can get innovation. You get lots of different people's ideas, and I hope I've showed you in some of these examples that some of these ideas are really novel and really very interesting. So not only are we generating the next generation hazard resilient pipeline, but we're also helping to do the next generation hazard resilient pipeline simulation models, because accounting for these geometric nonlinearities requires some special modeling processes, and I hope in this lecture you understand our philosophy in terms of how we're approaching that problem. So, pipeline system performance. Let's just take a quick view at the Canterbury earthquake sequence, reminding ourselves that this was an extraordinary event, about 1,800 buildings in the central business district of Christchurch coming down, 30 billion, that's US dollars, direct losses, about 20% of the forward monetary economical productivity of a country. This is pretty serious. So, it started with the September 4th earthquake, went to the big one, which was actually the smaller one, that was the Christchurch earthquake, or the 22nd February, at virtually ground zero. I mean, this was a few kilometers south of Christchurch and was a shallow-based earthquake. And if the Tohoku earthquake was a sledgehammer, this earthquake in New Zealand was a hypodermic needle, because it took all the energy from this earthquake and injected it right in the heart of Christchurch. And it tells you that you don't have to be in a big earthquake to get into trouble. You just have to be in the wrong place in the wrong time. And the consequences here were quite severe. There were another one on June 13th, another one on 23rd of December, and then one more recently didn't have a significant impact on a lot of the built environment, but it also produced some extraordinarily valuable data. So if we were to take our GIS shapefiles and actually plot those, these were all generated by Tonkin and Taylor that formed teams to go out and map the liquefied areas of Christchurch after each of the earthquakes of the Canterbury earthquake sequence. For the first one, the 4th September 2010, we got about 52 square kilometers. For the one that did all the damage, we have about 96 square kilometers. These are all very large, massive liquefaction type of effects. And then in the June 13th, we have a 91 square kilometers of effect. That's a lot of soil that's been affected by soil liquefaction. That 96 square kilometers is about 66% of the Christchurch area, of the metropolitan Christchurch area. Now, a lot of people aren't familiar with Christchurch, so I created a scale called San Francisco. And here's a map of San Francisco, and here are the shapefiles for the liquefaction zones measured and documented after the 27 February 2011 earthquake. When I move one on top of the other, you get a sense for the scale of the liquefaction in Christchurch. It was 1 Frisco large. So what the New Zealanders were able to do is they flew high-resolution LiDAR before and after each of these earthquakes, so that we actually have, and then, I mean, they also made this available to everybody in the world, by the way. You actually can go on there and you can get the settlement. So what you get with the LiDAR is you get a point cloud surface. And that point cloud surface, if it happens to be vertical, is a surface. Then you get a surface after the earthquake. You subtract the two surfaces, you get the settlement. And moreover, you can get the differential settlement, because these are on 5-meter spacing, so you can take the settlement at one point on the 5-meter spacing and the settlement on the next point, and subtract them from each other and divide by the 5 meters, and you get an angular distortion that can be linked with building damage or pipeline damage. Lateral movement, same thing. Here, they flew it on very close separations, 4-meter spacing here. And the beauty about this is that 4 and 5 meters are very consistent with the dimensions of pipelines, which are about 6 meters between joints. So the acuity, that is the ability for these measurements, these movements, to actually measure differential movement at the scale of pipelines is extremely good. Now, we know from the work of Bosgardine and Cording that you can take the horizontal strain and the angular distortion, and for tunneling and braced excavation purposes, evaluate building damage as a dual two-dimensional assessment. Because pipelines and structures are not just damaged by differential settlement, and they're not just damaged by horizontal movement, they're damaged by both simultaneously at the same time. So what we can do is we can take the records of the repairs and damage in Christchurch. We can take these white areas, which represent the zones of mapped soil liquefaction, the green, which represents the flights for the high-resolution LiDAR. We can import on that what the geo-coordinates of the water distribution system are for all the different types of pipelines, and then the repairs for all the different types of pipelines. And we can go 4 by 4 meter square or 5 by 5 meter square, count up the number of repairs, the number of kilometers of a pipe of a particular type, divide that into the number of repairs and get a repair rate, which we then can break up in bins and show correlations between the permanent ground deformation in terms of angular distortion or lateral strain and the repair rate with respect to the pipeline. If we do that, I'm going to say one more thing about the lateral strains. You get northing and easting at these 4 by 4 meter apexes, and that's a finite element, of course. So all we can do is take finite element formulation here, characterize the strain state from that finite element formulation, and then pick the maximum strain for the correlator, because that's a unique value representing strain field within that particular square. So now if we actually look at the correlations one at a time, we've got repair rate for different types of pipelines, asbestos cement, cast iron, PVC, plotted as a function of angular distortion only, we get very good R-squares. Now, of course, if you happen to take this particular relationship here for asbestos cement and you take it back to an angular distortion of 0, you're still getting repair rate. And you say, well, why am I doing that? Because some of those points were affected by lateral strain that you're not accounting for in that angular distortion. Similarly over here, but when you combine the two and you develop these linear relationships between lateral strain and angular distortion, and you color code this in terms of repair rate, you actually have a unified way consistent with the way we characterize building damage from ground deformations to take a look at the correlations that we would expect between pipeline repair and liquefaction in future earthquakes. Because it's fundamental when you look at it as angular strain and when you look at it as lateral strain. So now, if we now come back to the measurements in Christchurch, we can add up all of the lateral strain measurements, this as an example, or we could, tensile lateral strains, or we could add up all of the angular distortions. I'm just illustrating with the tensile lateral strain, and we can develop cumulative frequency plots. And there are millions of points involved in these cumulative frequency plots. And these earthquakes, because of what the New Zealanders did with the high-resolution LiDAR, are the biggest laboratory large-scale test we're ever going to get for a while on infrastructure response to liquefaction and in a way in which it can be quantified. And the types of pipelines that we've been testing at Cornell are able to accommodate tensile strains in this range of about 1.5 to 2. And when we extrapolate backwards to how they would have performed in New Zealand, they would have been able to accommodate about 95% of the cumulative distribution. We like to show the data this way. We like to qualify the performance this way because it's truly a system way of doing it. No pipeline can survive all the deformation that can be served up in a major liquefaction event. But you can build a shapeshifter that can accommodate most of it. And this helps us to quantify that, and the water companies seem to be quite comfortable with it. So there is our exceedance levels. All right, so lessons from Christchurch. I'm going to skip that. I'm going to go immediately to the last topic. Again, I don't want to run out of time, and that brings us to San Francisco. San Francisco is a city of earthquake-resistant buildings, Transcona Tower, some of these well-designed seismic structures, but a lot of people forget that 96% of the building stock in San Francisco are timber frame structures, which means that fire following earthquake is the big hazard here. Also, there's a huge wind in San Francisco, so wind and fire don't mix well, and that means we have a serious hazard. In fact, 1906 is still the greatest single fire loss in United States history, with 490 blocks of the city burning to the ground and another 35 or so severely damaged. What has happened in the last couple years is that San Francisco has passed 2 earthquake safety and emergency response bonds, one in 2010 for $412 million, and another one in 2014 for $400 million to fix their auxiliary water supply, which is their fire backbone of fire protection backbone in the city of San Francisco. And we used, in this first bond issue, the measurements from New Zealand to simulate what would be the behavior of the auxiliary water supply system and be able to accommodate fires that would be generated in San Francisco. And the way we did that is we went to the fire department, and the fire department said, if you want to run performance, spatially distributed performance, then you need to look at the response of the pipeline system relative to the fire demand. And if you're going to look at it relative to the fire demand, you have to look at the fire response areas. That's the way we characterize the fire demand in San Francisco, because each of these 37 or so fire response areas is centered on a fire station. So you can characterize the demand in terms of fire following earthquake, and Charlie Scawthorne, who was working on this project, who's very well recognized for this kind of work, did that. We used the water supply simulation models developed at Cornell. AECOM was using them, and these New Zealand models for correlating liquefaction-induced ground deformation with damage in the pipeline system to actually say what the water supply could perform, and we're looking at the 75 quadrant of the probabilistic response here. So anything that's looking at green, we're getting about 75, 80% or more in terms of being able to provide water for the fire demand. And that's a number of areas in the central upper northern part of San Francisco here where the current auxiliary water supply system is operating. But you'll notice up here in the North Shore, certain areas of the financial district and so forth, they're really not getting this kind of coverage. So what we did is we ran these simulations, which are performance-based, and we went to the board of San Francisco Board of Supervisors, and we said, look, here's what you got now. We're going to give you a plan where you make all this stuff in the top part. See up here? It all turns to green. And they looked at us and they said, nothing doing. Water supply is not just for the rich. Water supply is for everyone in the community. I was never more embarrassed in my entire life. We thought we were good people, right? We did a good job. We did a bad job because we forgot about all these folks down here. I mean, these aren't economic engines down there, but these are people who can burn to death and lose their property. And they said, you go back and turn it all to green, which we did. Social justice. So pipelines aren't just about water. And they're not just about buildings. And they're not just about lifelines. They're about us. We depend on them. And a lifeline may save your life. So, we are currently working with the University of Cambridge and the University of California at Berkeley with Kenichi Soga and his group. They actually used one of our very large-scale tests this last summer to proof of concept in terms of ground, extreme soil pipeline interaction ground failure for distributed fiber optics, both to measure pipeline bending strains and axial distortions, joint movement, time domain reflectometry to measure leakage, and then underground wireless to actually get the signals out of the ground. And we can compare them with our very good instrumentation results, and they compared extraordinarily well. So you can't have resilience unless you have intelligence. And I call this the IQ factor. We can take the best of our technology now, the best that we can do, which is some of these shape-shifting pipelines, and we can put them in the ground, and they have a high IQ today, right? They're the best that we can do. 20 years from now, they may be stupid. The only way you can keep up is to put intelligence into your systems, to be able to perceive what needs to be fixed, to be able to monitor things, and be able to have an integrated system approach to managing and improving your lifeline systems. So the last lesson that I'm going to talk about here is the intelligence. The intelligence and the community and the humanity of these systems are what makes them exciting and what gives us pioneering possibilities and what makes it an extraordinarily interesting and exciting field to be in. So I hope in delivering this Terzaghi lecture with my Terzaghi bandage on that I've been able to at least encourage some of you to follow up and look into this whole area a little more vigorously, because it really does a lot of good for a lot of people, and it's extremely interesting and exciting at the same time. Thank you.
sir.
Yes, sir.
First of all, thank you for giving us such a great lecture. And second, I have two questions for the suction effects in the unsaturated soil. So first is what's the approximate range for the degree of saturation for the soil data you generated that month?
Yes. So what they did, what the Cambridge group did is and it was a really good question. I didn't have time to get into the detail. They did the whole saturation curve, and they picked the maximum suction associated with the degree of saturation for that particular grain size distribution. So they picked the maximum. That's a unique value. Now, we obviously know that suction is both temporarily and spatially variable, right? You can have a rainfall that soaks through the ground. You may get the degree of saturation that you need at some locations. To get the maximum, you may be below. So in using that, we're getting the maximum, and that may be more than we actually would experience, but then you never know because it also varies as a function of time. So we pick the maximum because it's unique and it covers our options. It's safe for things that we can't predict.
And the second one is how do you evaluate the suction effect for well-graded sand, which goes through all the four areas identified in the plot?
Well, when we did our test, I mean, we have a fairly well-graded sand, and we do develop suction. We had suction meters and potentiometers and so forth in there to measure all of this stuff.
So that's why just for the proteins, because
That's right. I mean, all these sands were tested in situ, both by Tokyo Gas and ourselves, and then the model was generated to be generic, okay, and then validated relative to two types of sands at the degrees of saturation that they were actually measured at during the tests.
thank you very much.
Surely.
Other questions? What's the most common material for pipeline? Is it plastic? Is it cement? Is it cast iron?
Yeah.
What's the trend?
So the reality on the ground is that most of our water distribution systems are made of cast iron. 70% of all the water in Los Angeles, of their 7,000 kilometers of distribution pipelines, are cast iron. Of their 10,000. We have interesting enough, the same fraction for New York City. About 70% of the water supply in New York City is cast iron. Got West Coast, East Coast. There's variability elsewise. Where I'm doing a lot of work in Portland and in Seattle, and they're up about 60% to 70%. Oh no! Everybody would love to if everybody could wish cast iron out of the ground yesterday, they'd be very happy about it. If you could figure a way to do that, you could be more rich than Carlos Slim. But no, that's part of this is building backbone systems. Nobody can replace 7,000 kilometers of cast iron overnight, and nobody wants to. But what you can do is you can selectively, based on the hydraulic network modeling, build backbone systems of the more ductile pipelines, strategically orient them relative to sources of water, such as swimming pool concentrations, lakes like Ivanhoe Lake and so forth in Los Angeles, and actually put together a pretty good backbone, only building or renovating about 10 to 15% of that system.
Any other question? Everybody's happy.
Good.
Let me.
There will be an exam on Monday.
So I would like to give you this plaque, and it reads Certificate of Appreciation to thank Dr. Thomas O'Rourke for delivering his 2016 Terzaghi lecture entitled Ground Deformation Effects on Subsurface Pipelines and Infrastructure at the occasion of the 25th Buchanan Lecture, Texas A&M University Zachary Department of Civil Engineering.
Pleasure.
Thank you
Thanks,
very much.
thanks, Jean-Louis. Thank you very much.
Now it's my pleasure to introduce Jonathan Bray, who is the faculty chair in Earthquake Engineering Excellence at the University of California, Berkeley. Professor Bray earned engineering degrees from West Point, Stanford, and Berkeley. Dr. Bray is a registered professional civil engineer and served as a consultant on several important engineering projects and peer review panels. He has authored more than 350 research publications on topics that include liquefaction and its effects on structures, seismic performance of earth structures, earthquake ground motions, and earthquake fault rupture propagation. He leads the Geotechnical Extreme Events Reconnaissance Association called GEER. He was in Seoul, Korea recently, and I learned that in his previous life he actually kept South Korea and North Korea apart and happy. Maybe you can share some of this with us in a minute. The title of his Buchanan lecture is Turning Disaster into Knowledge. Please help me welcome the 2017 Buchanan lecturer, Professor Jonathan Bray.
Well, thank you. It really is an honor to be chosen to give this lecture. Jean-Louis, I really appreciate the invitation as well as from the rest of the faculty. It's been a joy to get to know some of the students at Texas A&M. It's a wonderful program, and it's just spectacular to be here today. And I'm going to talk about turning disaster into knowledge. That's actually the tagline for this GEER activity. It started as geotechnical earthquake engineering, but we transitioned to geotechnical extreme reconnaissance, and it wouldn't be possible without the National Science Foundation and then all the people who actually get the work done. From this area of the country, you don't need me to talk to you about that incredible rainstorm that you had. You know, over 40 inches of rain over several days in Houston, just east of Houston over 50 inches, and I think the record was over 60 inches a little further to the southeast. The city could not accept that amount of water over that time period without the flooding you see here. GEER got into action because this was an important event, and the focus was to have two teams, to have a team that focused on the flood effects, but the flood effects on geotechnical structures. And as you can see here, as pretty clearly by the color, the maroon color, which I saw a lot of today, and this is Marcus Razzullo, that you had the Aggies here. You had the Aggies going out during this difficult situation and trying to document these important lessons. This is perishable data that needs to be captured and to look at performance of geotechnical structures affected by this flood event. And this team led by Lee Wooten of GEI in Boston has already developed a number of recommendations, a number of findings and observations, and the report is not even out yet. And as this information comes forward, it's going to be very effective in terms of moving forward. Similar to that, Nina Stark focused on the coastal effects and looking at issues in terms of scour, in terms of the development of the runnel and ridge that developed in front of this water protection system of rockfill, and looking at scour effects. And it's not quite as obvious, but here's another Aggie doing great work collecting data in terms of scour effect. And they have a number of important observations and such. So this has been an active time for GEER. This has been events that I haven't gone to. These are events that the GEER Steering Committee thinks we should go to, and people localize locally, or they come in with their expertise and they capture this data, and we move forward from that. Then we have the Mexico City earthquake. We had a magnitude 8, and we were about to send a team to that, and in fact they were mobilized to go, and then we had 32 years after the very infamous 19 September 1985 earthquake, we had the magnitude 7.1 that caused damage in Mexico City. And we rerouted Kevin Franke and his team and said, you're now the advanced party. And we're going to have a secondary team come in with Tara Hutchinson and others to be able to capture that. The thing that was remarkable, I was actually in Korea. I think it was around 3 o'clock in the morning when I woke up because of this earthquake alarm and started looking at this. And Ellen Rathje, who's the UT head of NSF-sponsored Design Safe, is scouring the internet, and within a few hours after the earthquake is sending me things like this. So we actually, besides recognizing the importance of this event, we started to realize that there's a whole new world in terms of capturing data, in terms of seeing how structures with soft stories respond and understanding how these type of structures are developing. So having these pictures and having regular people essentially capture this information is it just remarkable in terms of the data that can be produced, in terms of understanding how structures respond to the ground shaking, which is a key element of the Mexico City shaking. People knew that this was an important earthquake because of that magnitude, the earthquake that occurred in 19 September 1985, where over 10,000 people were killed because of the lake conditions. This was a lake that was been filled in by humans, and so we have very soft soils of different thicknesses. And because of the different thicknesses of these very soft soils, there's a recognition that there's ground shaking in the hills. In fact, there was an earthquake workshop in San Francisco, in Mexico City at UNAM. They didn't actually stop the earthquake workshop until they started having all their beepers going off, because the ground shaking was relatively benign, 0.02% of G. But in the soft area with the amplification of shaking and having the structures on top of that respond to it is where they had all the damage. Because of that, they have mapped areas in terms of the firm ground and then some transition zones where you have different thicknesses of the lake clay, the soft Mexico City clay, and then the lake area where you have the deeper deposits. And so each of those, with their stiffness, because of their stiffness and their thickness, are basically going to have a natural period that they like to amplify the ground shaking. And in fact, this work would not be possible without the interactions with our colleagues at UNAM. Juan Mayoral is the lead professor working with Tara Hutchinson and Kevin Franke. And this is the initial building statistics in terms of the damage. Primarily 5 to 8-story buildings were heavily damaged in this zone, this transition 1, transition 2 zone, or the edge of the lake bed. And so capturing this data and understanding which buildings did well, which buildings were partially collapsed, which ones collapsed, and where they were collapsed is going to be incredible in terms of doing 1D, 2D, 3D modeling and capturing. So we have to capture that perishable data to learn from it, and that's what they're doing now. I'm working as a peer reviewer on the new airport in Mexico City, and one of the issues is, will we develop significant pore pressures in these Mexico City clays? There's a certain threshold strain that is fairly large because of the high plasticity of that clay, but eventually you could capture high pore pressures. Could we have water come up along the piles? Could we have foundation issues? And there's some records of that in the 1985 Mexico City earthquake. So they're deliberately looking for those cases. They're trying to find cases where foundations, where piles pulled out of the ground, where foundations tilted, and this is one of the buildings that they've located so far where they actually have differential settlement. So there is ground failure issues to look at. And they also found a number of cracks at the edge of the transition zone toward the lake zones, and you can see the crack if you look carefully through here, and this is what they look like on the ground. So the key thing here is to capture this perishable data, understand where it occurs, and then we can figure out why. And so those are active things that I expect you to see lessons come out from. So GEER has been active because we understand, and the people who volunteer for this, they all do this work pro bono, they realize that geotechnical engineering is an experienced, driven field. I noticed your first invitee for a Buchanan lecture was Ralph Peck. I mean, who could you have better than a leader who understood the importance of good laboratory testing and analysis, but always couched with field case histories and the observational method? Because we recognize, as good as our tools get, and we want to keep on working on them in the lab, the centrifuge, the shaking table tests, and the computer, we're never going to capture all of the issues in terms of the natural response of natural soil deposits. And field observations shape our understanding, and they provide the data for things such as liquefaction triggering, lateral spreading. But it's personal. I and a lot of people probably would have been on the Cypress structure around 5 p.m. on Tuesday, October 17, 1989, except for the fact that I and a lot of people cheated and went home early that day because we wanted to see the Oakland A's play the San Francisco Giants in the World Series. What's the chance that a major earthquake hits the Bay Area and the Oakland A's are playing the San Francisco Giants in a World Series game that starts at about 5:04? So at 5 o'clock, I and a lot of people were in front of their TVs waiting to watch that game. This is the route that I took back from Berkeley that day. That's what the superstructure looked like before the earthquake hit, and unfortunately, this is what it looked like afterwards. 41 people were killed. And I should hesitate to say only 41, but it would have been probably 410 or 500, because normally at 5 p.m. on Tuesday, that was bumper-to-bumper traffic. So we were very lucky there. Now, the structural engineers in the room will talk about, well, that structure is poorly built. It has poor ductility and it has details. But that superstructure only failed on top of the soft clay. It didn't fail on top of the firm ground. So again, it's not just the structure being poor, it's the energy and the shaking and the intensity being amplified on those soft soils. In fact, this became the earthquake of bridges. We had the Bay Bridge, which has cost us $6.4 billion to replace, which we finally replaced about 25 years after the event. And there were other bridges. You don't recognize me here because I'm camouflaged, and I'm a little bit leaner. And, but it's the same issue in the sense that we often didn't think about ductility, that same ductility we think about in terms of columns and beams and buildings. We need to have that same ductility between our bridge decks and our piles or bents. And so capturing this data is critical. I learned another important lesson. In fact, I learned this being one of a family of 9, is never ask permission because you might hear no. We sent teams of people down there. We were actually the 4th group to show up there. Everyone else was turned away. So I didn't ask the Caltrans inspector there and the police officer guarding the bridge whether I could have access to the bridge. I came there in my uniform and said, "I'm here to see the bridge." And they just waved me through. As Dr. O'Rourke mentioned, and damage in San Francisco was severe. Again, there are soft story structures that did not fail on firm ground, on rock, in the Presidio area and other places. The soft stories that failed were in the Marina District and other places that had these soft soils. It's the soft soils amplifying the shaking for these soft stories. And the fire that started was in the Marina District. And Professor O'Rourke can talk about this at length, and I know from talking to Professor Raymond Seed, who was working with the fire department there, I know from running in terms of the physical fitness test that we used to have to do in the reserves, it's always windy in the Marina District. If you want to go fly a kite, that's where you go. I think there's 6 days out of the year where it's not just a stiff breeze. That just happened to be one of those days where there wasn't a wind. If there had been a wind, there are some points that people said they would have pulled back to Divisadero to fight that fire. In fact, when I first got to the Bay Area and talked with people that were in their 80s and 90s, and I asked them about, were you here for the 1906 earthquake? They go, you mean the 1906 fire? They remembered it as the 1906 fire, because the earthquake lit the match, but it was the fire that destroyed their city. They can remember as young people walking up to the hills to look back and see their city being burned. Then we had the Northridge earthquake, January 17th, 1994, and similar to what they saw in February of 9th of 71, they had strong shaking and damage to infrastructure. We had pulse motion, slope instability. I guess one positive side is the way of driving rent down. But unfortunately, 57 people were killed. So we have 63 in Loma Prieta, 57 in the Northridge earthquake, and those were not direct hits. The Santa Monica Freeway is, at that time, America's busiest freeway. One of its overpasses was taken down, even though it was some distance away from the zone of energy release. The place where it went down was named La Cienega, which is swamp. So again, we have a number of these overpasses, similarly built, similarly designed, and yet the one that fails is because the ground conditions are so important to the performance of that structure. You learn some scary things. You learn great things about people in terms of responding. And Houston Strong, it was amazing seeing how people responded to that event. This was scary. This was actually storage facility where when this collapsed, we had access to it. I saw AK-47s, Claymore mines, and rocket launchers. What somebody in Los Angeles, why someone in Los Angeles would have that kind of equipment, I don't know, and I don't even want to think about it. As Professor O'Rourke mentioned, I mean, one of the key issues is ground failure, which breaks your gas line. This gentleman starts his truck, he ignites the gas fire, and you can't put the fire out as these things burn, these buildings burn, because the water has lost. If you lose your water suppression, you can't fight the fire. If you lose your ability to fight the fire. And in fact, this is another broken water line. Then we have the 1995 Kobe earthquake. They were well aware of the major subduction zone earthquake. They'd had their Cantu earthquake in the 1920s, and so they focused on that. This was an area where they did not appreciate the importance of a direct hit. Yet this earthquake hit them, and the people who had gotten fairly confident that they wouldn't have the problems that they saw when they visited us in '89 in San Francisco and visited us in 1994 in Los Angeles, they lost 6,434 people. A modern country, one of the best in earthquake resilience, lost 6,434 people. And I can show you time histories, but I think one of the ways to show you is an actual recording of what that ground was like. The seismologists had talked about forward directivity, pulse motions. This was us seeing it. It wasn't the normal ground shaking that they were thinking about in Japan. Some earthquake far away where they got maybe 2 minutes of shaking, but it was fairly low in intensity. This was all of this energy coming at them in 1 or 2 pulses. And after surviving those 1 or 2 pulses, it only took maybe, if you look at the clock here, it only took about 6 to 8 seconds for that earthquake to deliver all of its energy. So that really changed the way we did things. Those 6 to 8 to 12 seconds of strong shaking led to massive liquefaction. In fact, 19% of the import-export traffic came through the Kobe harbor, and they had 186 berths in which to offload traffic. It was amazing to see plastic hinges and see collapses of these structures and to see massive liquefaction, as you see here with the lateral spreading. Out of that 186 berths, all but 8 were taken out of commission. The 8 that were not, they realized it wasn't just fill on top of soft clay and being delicate. They realized that they had potential things with liquefaction, so they had done ground improvement ahead of time. Now that the traffic has moved to Osaka and other ports, it hasn't come back in full capacity to Kobe. Actually, this is where the other key is networking. Professor O'Rourke knows Professor Hamada. Professor Hamada knew somebody, and we heard about a subway station that had damage, and that was a thing that we had not seen failures of in terms of buried structures. So through that connection, Professor O'Rourke and myself and Professor Kenichi Soga, who was Kenichi at that time, not a doctor, and Liam Finn were the only 4 people allowed into this, and we saw that the ground deformation and the racking load, just the structure did not accommodate that. It did not capture, it didn't have the ductility because they hadn't thought about the liquefaction induced and ground strain from the near fault ground shaking. And probably the most disturbing thing was the fire, because most people died because of the fire. And in fact, when I was taking this picture, a young lady put her roses next to a picture of her mother and father, and you realize every person has a story. In fact, since Kenichi Soga had spent time in Kobe because he went to Kyoto, we talked with people, and you say, well, only 6,000 people died out of a large pit. Everyone was touched by death. Their brother had died, their mother had died, their sister had died, their cousin had died, one of their schoolmates had died. This city of 1.5 million, everyone felt it, and it was depressing to walk around and see a resilient people broken by this event. We can't let this happen. And so the objectives of PEER are to collect this perishable data. It's terrible that these disasters happen, but it would be worse if we didn't learn from them and therefore we need to turn disaster into knowledge. We need to develop new and implement new technologies, and the whole idea is documenting these effects so that we can advance the profession. At the top of this are the volunteers. The GEER members and volunteers, which is greater than 400, they go to the website, they say, these are my skills, I am interested in going to the field, I am interested in participating in this. I will give up a week of my time in the field, and for every day in the field, you got a day in the office that you have to pull all the notes together and produce the report. I will give up 2 weeks of my life because this is so important. And it's so important for the profession, but it's also so important for you to learn these lessons, to see these things. I remember in Kobe, I couldn't believe what I saw. And I look around and I see Liam Finn and I see Ed Idris, and they're as shocked as I am. And I realize that's not the last shock I'm ever going to see in my life, that I need to go to these events because I need to be reminded the next time I'm pushed by a client to get close to the edge, what being over the edge means in terms of affecting infrastructure and people. To help steer this and decide whether we're going to go or not and what the size of the response would be, we have a diverse GEER steering committee which brings in people from different backgrounds in different parts of the U.S. And then we have an advisory panel, and in fact it includes Professor Tom O'Rourke and others who are geologists, social scientists, structural engineers, tsunami experts, to be able to help us respond to these events. And in the end, nothing happens at a university without a graduate student, which the GEER recorder now is Estefan Garcia. These are some of the recent reports. In the end, you know, there's an internal development, there's a lot of things that are positive, but our lasting legacy are these reports. And so I've highlighted in yellow those that are non-earthquake, because we started off just focused on earthquakes, and then it was actually Katrina and what it did to New Orleans. We realized the same kind of techniques we're using to collect that data in the field can be used for non-earthquake events such as a hurricane, or a landslide like the Oso landslide, or storms such as the Central Texas floods in 2015. And actually Nina Stark already has the Hurricane Harvey coastal report out, and you can look at that and learn from that. And the other reports on Hurricane Harvey flood, Hurricane Irma, both in the south and the north, and effects on Florida, as well as Hurricane Maria, are going to be up there shortly, as well as I've seen an initial draft of the Mexico City earthquake. So the first thing that we do as the GEER Reconnaissance Steering Committee is we have to decide whether to respond or not. We don't respond to every event. We respond to those events that are going to help us move things forward. But we first stand back and look at safety. If we don't think people can work safely in the area, then we're not going to send people and put them in harm's way. We also say, will it add critical new data? Will we have the opportunity to test or learn a new hypothesis? Can we have an event like that in the U.S. so the results are directly applicable, like they are in New Zealand? Quantitative data, one of the first things I look at is, do we have strong motion sensors? Do we have surge gauges? Do we have that quantitative data that's going to allow us to make an excellent case history? And then what's the likelihood of follow-on research? In fact, NSF is very clear in saying if you do all this great work and there's no follow-on research proposal from that work, maybe it wasn't so cutting edge. In terms of the principles of reconnaissance, I actually first learned how to do reconnaissance as a Corps of Engineer officer in Korea. That was my primary job, besides building things and others, is just general reconnaissance, getting a sense of the lay of the land and being able to provide the eyes and ears to the battalion and to the other division assets. So the first thing to do is, what's the overall assessment of damage, identifying key opportunities. Asking yourself always, if we do this, if we document this, we take the care to do this, will it advance the profession? If a loose, saturated sand that's incredibly loose, is strongly shaken and it liquefies, do we care? We know that that should happen. And a very, very dense sand that's very lightly shaken. We want case histories that are on the edges between good and bad behavior. We want to document good behavior as well as bad behavior. We remind ourselves, it's kind of one of our mantras, is one well-documented case history that will get into a thesis and then get into the literature and then be used by engineers 10 years from now is so much more valuable than a bunch of photographs of damage. A team approach and systematic collection of perishable data is critical. You want to use remote sensing in UAVs. Everything's geocoded. And very importantly, while it's useful to think of possible mechanisms, you cannot figure out how something failed while you're in the field. You will collect the data to confirm your hypothesis. It's so critical to, even if you believe someone, what they said, challenge them and say, let's collect this data and collect that data. It's so important to just collect the data, get the facts. There's always time to figure out the why. This is, again, a thinner me. Right after the August 17th, I started believing that all earthquakes occurred on the 17th of any month. My birthday is on the 17th, so I thought there was coincidence there. But this was, we landed on the big airport in Istanbul, and we went directly to the small aircraft airport, and we got up in the air. Darren Ural was instrumental in getting us up there. Once we flew over Adipazari, we knew that just incredible amount of damage there. We need to go there. This is the Chichi earthquake. My dissertation was on earthquake fault rupture propagation through dams. So when I see a dam that's been offset by 9.1 meters of offset, I'm excited by that in terms of learning from it. An important lesson I learned here is helicopter rides in 1999 in Taiwan were expensive. $3,500 an hour, $3,500 an hour. I got a deal because I knew Joseph's son and he knew somebody in the government because his father was an assistant prime minister. I got this helicopter for $2,500. Steve Kramer, Norm Abramson, J.P. Bardet, Les Harder, myself. 2 weeks after we flew in this helicopter, it crashed. They did an investigation and they found out they weren't doing their maintenance. So as much as I like to save the U.S. taxpayer dollars money, I will never get a deal on a helicopter ride again. I will pay full price for the best helicopter. One of the best helicopter rides was this. I knew that the Navy and the Marines had come to Turkey to help in the relief effort, but it had been 7 days, and they were not going to find any more people alive in the rubble. So I know what military units, having been in the military, when they're waiting for their orders, they have nothing to do. So why don't give them something to do? I said, you know, I expect you to have observation helicopters. Can you come pick us up and we'll fly over Adipazari and do some very careful photographs with a Navy cameraman? And they said, sure. And so everyone wanted to go on this, but I said, you know what, we'll take Professor Rathje. And we only have room for Professor Rathje and me, and the Navy photographer, so that's it. I expect to see an observational helicopter like I used in Korea to come. But no, they send a Super Stallion. A Super Stallion holds a platoon of Marines. It's not only a Super Stallion, it's the Super Stallion because it had stenciled on it. This was the helicopter that landed under fire in Bosnia and picked up Captain Scott O'Grady, who was shot down in 1995. So my son never really respected me in terms of all the work I did, and you took soil and you moved it around. But when I brought back this picture, and he had just finished reading the book about that Captain O'Grady, he goes, okay, Dad, you're cool. This is my safest ride. 2 police officers with 2 weapons each. Okay, so flying in a helicopter, I feel really safe when I have 2 pilots and they both have pistols. The thing that was dangerous about this is I learned that the camera they have on the front of the California Highway Patrol chip thing could see a license plate at a distance of 2 miles and read the numbers. So since then, I have slowed down on Highway 5 going through Central California. The other thing, though, but you know, mostly helicopters are nice because you can hover. They would not hover because when you're just hovering and you lose your engine, you basically are a rock. They would always go forward. Their idea is always flying forward, but that changed things in the sense of how we had to go on the fly to be able to get the aerial reconnaissance done with the photographic equipment that we had. And my most recent ride was actually working with GNS Science is after the Kaikoura earthquake to see the landslides. I mean, there's just massive landslides. To get an overall perspective of one of the major highways, Highway 1 being essentially buried by this coastal slide, this large slide, not really fully realizing this is a slide until you can see it, and then you can actually land next to it and then look at it. And then the damage to the port of Wellington, which you can see very closely. Some of the ground is lost here, and you can see ejecta on here. And one of the great things about a helicopter is you could land it, get out, and make measurements. But the future is now, and the future is a UAV with a photograph. This is from the South Napa earthquake. This was done by Tara Hutchinson and her former graduate student, Chen, who's now a professor. You can see the fault rupture right through there. So not only being able to capture this data and having it recorded, but to be able to, when you get to a site, to get up in the air and look over the site and go, oh, look at this fault rupture right here. Look at how it comes through these structures. To get this overall sense of what's happening, that's so important. And the thing is, now every team can have their helicopter ride. Every team can send up a little team and capture this data, but see the ground deformation, get that overall perspective. Because I've always felt from the air you get a sense of what's going on, then you can basically get into the ground and look at it. And it's amazing where we used to use LiDAR all the time, we can now start saying, this is work done by Demetrius Zakos at the University of Michigan. He's not able to get on this site safely. It's physically inaccessible. But what he could do is he can have, instead of spending days, he can spend 3 hours with his UAV. He can take 649 high-quality photographs that have markers in them so he can survey in those markers and have different points of view. And by having the different points of view and knowing where the camera is and knowing the object that they're looking at, it can be reconstructed with this concept called structure from motion. And therefore, everyone can not only see what the ground looks like from above, they can actually develop high-resolution, detailed mapping. And then once you have this, you know what happens. And then you can deposit this in design safe, and then people can use this for the future. Before structure from motion, which is now almost opened it up to everyone, we had LiDAR, such as what Professor Tom O'Rourke talked about in terms of Christchurch. This was the only way to really capture the ground deformation from the Oso slide, where unfortunately in March, 43 people died in 2014. This was a large slide. It had moved a few times, so they actually had a LiDAR survey done in the early 2000s. Then they had done one in 2013. So of course you can come back and redo it in 2014 after the failure, and you can understand where the ground has accumulated, where the ground has evacuated from, and then that gives you the data that you can then train your material point method or your analysis to be able to capture that data. It doesn't have to just be from the air, but you can take the same type of technology and put it on the ground. Rob Kahan has been a key player in terms of this ground-based LiDAR, but just like you see a picture, every pixel in this LiDAR image is got the same thing in terms of a pixel, but it's located in XYZ. So once you have that data, now you can cut it, you can do cross-sections. So I saw the Corps of Engineers doing normal surveying after Katrina with the dumpy level and getting lines, and I called Rob Kay and I said, you got to come out here, because he was able, before the levees were completely eroded, he was able to capture complete descriptions of the ground deformation. Remote sensing is critical. The satellites, Professor Rathje's done a lot of work in this area, Professor Frost as well, and others. But the only reason we went to Las Palmas Dam, which is a tailings dam which unfortunately liquefied and killed 4 people, is because we saw this image. It took about 5 hours to get to this site, and it was in a very inland area, so it just seemed, and you also don't see it from the ground. You have to be up to be able to see the scale of this liquefaction flow failure. And Google Earth is amazing. I remember when I was in Turkey, I would have done anything for a map. I just could not get maps. In fact, you know, the best place in 1999 to get topographic and geologic maps of Turkey were from a website in the Soviet Union. I don't know why the Soviet Union would be interested in Turkey, NATO and missiles and all that stuff, but that was the place. So we got some information from this website in the Soviet Union. Other times, I actually had a camera that I had hanging from my chest that I'd walk in and I'd say, do you have any maps? They go, no. I go, I see a map on the wall. Well, that's not, you're not allowed to have that. I'd take pictures. In fact, the Turk who was with me goes, Professor Bray, he goes, you scare me. But we did anything just to get a map. So without a map of Adapazari, how can we map the damage? How can we know where we are? Well, now Google Earth, I could walk over this ground. This is taken on the 26th of February, 2011, just 4 days after the 22 February magnitude 6.2 Christchurch earthquake. You can see the liquefaction. You can unfortunately see this collapsed building where over 100 people died. You can see that, and therefore you can walk the ground. I had been to this location, but I had not been to Turkey in that area, and I had not been to the area in Taiwan, in the middle of Taiwan, before I got there. I'd have loved to be able to do street view and walk it. Even though I had been to Christchurch a couple of times before this earthquake, I spent some hours just walking the streets of New Zealand, Christchurch. So when I got there, it had been like I had been there just recently. And it's also interesting to kind of go back and look, because there was an image on the 15th of February. So that's before the earthquake. You can see the non-collapsed building and the collapsed building. And then if you're worried about resilience and reconstruction, you can watch with the time version how the city is responding, how the city is building back from that event. Everything is now geolocated. Everything's digital. The idea of taking slides and handwritten notes, those days are gone. And you can pull everything together with Google Earth. You can pull everything together with DesignSafe. You need to be able to share data, and that's a key element. Everything has got GPS these days. In fact, here's a good example where you've got, the overall map, you've got the location, you've got the lat long. You can reoccupy that location. So talking about earthquakes, I'll use 3 examples, 2 older earthquakes and a more recent earthquake. One of them is Adapazari, Turkey in the 1999 Kocaeli earthquake. You recognize a lot of Turkish names. We always work with the in-country people. Unfortunately, this event killed over 17,000 people. Adapazari is called Island Market. So it is an area that's actively fluvial. And so the river that's here used to be over here, and so you can imagine that think about the Mississippi area. This area has been things like a fire hose has gone back and forth across this area in deposited soils. So it's interesting to look at the damage statistics. The cold colors are fewer than 5% damage. So like we normally see, the buildings on rock did well. They were strongly shaken, but they weren't as heavily damaged as on the softer soils. And a lot of this has to do with liquefaction. And one of the key issues here is looking at areas that only had 15 to 30% damage versus 30 to 45 versus more than 45%. Can we understand that? So we decided, okay, let's do lines north-south, and east-west across this area and capture this perishable data. So this is just a subset of the hundreds of buildings that we looked at, and these are 60 structures along a section of line 1, where using a rapid survey of saying, building by building on a street, is there any ground failure? Is there minor ground failure, a little bit of liquefaction, less than 10 centimeters of settlement, moderate or severe? Severe is some lateral spreading, more than 3 degrees of tilt, or a settlement more than 25 centimeters with severe liquefaction. And then what was the damage? What was the effect on the structure? And so we don't have time to do a detailed survey. We'll do that of selected buildings. But this is a rapid survey of no damage, architectural cracking, minor structural damage, cracking of structural bearing members, significant damage, so actually plastic deformation across those cracks, partial collapse, collapse. And what you see is poorly built buildings have problems, but there's fewer of these poorly built buildings failing in this area, and that's where there's no observed ground failure. Once we have that data, and that data was gone several months after the event, now we can come back a year later with NSF funding, peer funding, and we can do site investigations. And we can start to figure out, does this make sense or not? So cone work, some borings with an instrumented SPT. Then we can look, and if we make a change, and a very, very important change, we can say this ground with that important change has non-liquefiable soil over liquefiable soil. This should not have liquefied, and this has liquefiable soil over liquefiable soil. So we start patting ourselves on the back. We sit there and go, but there's an important change. What the state of the practice was at that time, based on the 1997 workshop, so before this event occurred, was let's readopt the modified Chinese criteria. which has a major deficiency that actually Arthur Casagrande pointed out in 1937. It's not the size of the particle that matters, it's the mineralogy. If you have very, very, very fine quartz in feldspar that is smaller than 5 microns, it doesn't act like a clay. It acts like a silt, and it can liquefy. And so we have a lot of cases of high clay content in terms of size liquefying, because it's not size, it's mineralogy. So that's why he developed the Atterberg limits and used the Atterberg limits. It didn't develop, but it used them to basically classify soil. So he used plasticity. So we came up with a plasticity-based methodology for saying soils that should be susceptible to liquefaction and those that are not. That came directly from that event. The 2010 Chile earthquake, we thought that was the major subduction zone event, hopefully was, for our lifetime. And just a year later, we had the magnitude 9 Tohoku earthquake in Japan. But we mobilized people. If you recognize some of these people, like Pedro Arduino, a lot of them are from the Pacific Northwest, because that's the event they're worried about off the coast of Oregon and Washington and British Columbia. I've highlighted those people that are Chilean. We could not have done this without Ramon Verdugo, Christian Ledesma, and Terry Eldridge, and the rest of these people. We even got, because somebody had an uncle who knew somebody in the Chilean Air Force, we even had the Chilean Air Force. We'll take anyone on GEER as long as they will contribute. They wanted to know where the damage would be. We said, we as geologists and geotechnical engineers can tell you where we think the damage will be. Okay, come fly with us. Okay? Unfortunately, 550 people were killed. Why this event was important is because we'd had a number of earthquakes that were intense, but they weren't of long duration. This thing was relatively intense, but very long duration. And so that's why we mobilized for this event and the Tohoku earthquake. I felt when I led the main team in terms of capturing this data that I was doing the Northridge earthquake, the Landers earthquake in 1992, and then the Loma Prieta earthquake all at the same time. In fact, I got really good at texting, because when you're driving through mountain roads, you could send GPS coordinates to team members and say, go here, and they can go there. And so communications are critical. One of the most important things was right off the bat, we started with meeting with our Chilean partners and understanding what was the geology, where are the maps, where do you think there's issues, and then getting up in the air. And the orange lines are the aerial reconnaissance, and then eventually you need boots on the ground. You need people to actually go to the site and make the measurements. So, for example, Kyle Rollins, working with others, doesn't just take this picture, but he takes the time to do detailed surveys on a couple of lines so that he knows I can develop this as a lateral spreading case history. Then he gets NSF money and he goes back a couple of years later and he does CPTs along this to characterize the site. So the whole idea is you can't have the case history without that perishable data. And it needs to be quantitative, not just qualitative. Then you're always surprised and you're looking for new things. And one of those new things is Caltrans was always worried about, could a drilled pier from a bridge sink into liquefied material? That's no longer a theoretical question. The Juan Pablo II bridge had liquefaction at depth. The liquefied material came up along the drilled pier and it settled on the order of 1/2 meter to 7/10 of a meter, causing the deformation you see here. And then I'm very interested in soil structure interaction, and that means you have to have soil engineers like Bray and Arduino, and you have to have a structural engineer like Tara Hutchinson, working with a structural engineer from Chile, to be able to document a case history completely. We spent all our time on the outside of the building, looking at ejecta and measuring deformations of the building relative to the ground. Tara and her fellow structural engineers spent all their time inside the building, documenting cracking of coupling beams and other types of wall systems. Then you can put all that together, and now you have a case history that says, on these ground conditions, which we can later go back and capture, we've done that through CPT and Schreitz weight sounding, we can sit there, can we capture this 40 centimeters of settlement, this about 30 centimeters of settlement, and this 10 centimeters of settlement, and the twisting and rotation which damaged that coupling beam. And then last event to talk about is the 2010-2011 earthquake sequence. Professor O'Rourke already talked about that. First, it would not have happened without Professor Mieszko Czubunowski of the University of Canterbury. Russell Green was the leader of the GEER team from Virginia Tech. I jumped into this thing. We had Brendan Bradley, we had Professor O'Rourke, just et al. It's a host of people that made this possible. And I was actually doing centrifuge tests, and it takes a lot of work to build a device and build an experiment and do that test. I was doing this at UC Davis. You're not going to just shake it one time. You're going to shake it with a lower intensity motion that the pore pressures just build up a little bit. Then you're going to shake it a little bit more intense, and you're going to shake it a little bit more. I left Davis and went to New Zealand because they were doing full-scale 1G shaking table tests because they had the magnitude 7.1. So it wasn't the Loma Prieta earthquake or the Northridge earthquake. It was an earthquake sequence. The same ground, the same structures were being attacked multiple times, and it's invaluable to have that type of case history. It was the most widespread liquefaction that I'd ever seen. And in fact, the only time I've seen something like this was in a snowstorm in Buffalo one time when they piled up the snow after the event. But this is sand taken by people from their yards and their houses and brought to the streets to be carried away. It's one thing when liquefaction takes your ride. It's another thing when it takes your throne. If you look here, it's not just the sand, but one thing I recognized after having been in Katrina, this was a flood event. That's the water line. These people had had a lot of damage for September 2010. They finally dug all the sand out. They got rid of all the damaged carpet. They moved back in. They celebrated Christmas. They kissed their significant other, or they call them partners there, on Valentine's Day. And then just a few days later, they had the 22 February 2011 earthquake, and it happened again. And it happened again on 13 June 2011. And people moved from this city. It was the second largest city in terms of population in New Zealand. It became the third largest because people moved out of the area. They got fatigued by liquefaction. I focused on the central business district and looked at buildings that slipped, tilted, differential settlement, pile-supported structures where the ground moved down, but very importantly, structures that had no damage or any negligible damage, even though there was liquefaction, because they had drilled piers that took it to the greater depth. I didn't know that at the time, but I said that's important. Liquefaction at the site, yeah, I see no structural damage. We can figure out the why later. And one of the things you realize is Christchurch is a little bit like California in the sense that most of San Francisco, the Frisco scale that Professor O'Rourke mentioned, was developed after something happened in 1849. Okay? It was the gold rush that brought everybody into San Francisco, and it just ballooned in size. And so most of the development in San Francisco has been over the last 170 years or so. Same thing with Christchurch. So it's great to go back and look at a geologist named Black, so it's called the Black Maps of 1850s, where he mapped what you had in terms of buried streams. You don't see those streams on the 21st of February 2011, but you see where those streams were on the 22nd of February 2011 because those streams are resurfaced by liquefaction. The shallow buried stream channels now are basically liquefying. That's where we have most of the damage. In fact, I'll focus on this CTUC building. I learned much from this one book called Christchurch, Swamp to City. That's what that city looked like in 1850. And so it's very important to remind yourself of that when you're basically looking at the ground damage. The survey of the CTUC building was actually captured. I didn't have structure for motion or LiDAR at that time. I basically found that I could go to Home Depot and buy a laser level, and by putting it on a platform, I learned from Surveying 101, I could basically measure differential settlement. There was a pipe that connected this building, which did not punch into the ground, relative to that building. It moved 60 millimeters relative to that one. And then I can measure the differential settlement between these bays that were separated by about 4.5 meters. And you can see it's relatively low angular distortion until you get to the last two bays. What's special about the last two bays? We're going to find out. And it's not surprising to see cracking. And of course, there's the extra damage of the ejecta. I saw very quickly that the ground conditions were highly variable in Christchurch, so we did closely spaced CPT across this feature, which had severe liquefaction, and this is where that shallow stream channel was. It's not there and it's not there, but it's right here, and it just clips the edge of the building. And so that's why we had so severe settlement on the edge of the building, the southern part of the building. In fact, these are the CPTs on the south side, in the middle, on the north side, and then on the north side of the other building that we're using as a frame of reference. I've highlighted it in orange, those areas of silty sands that should have liquefied by our prevailing techniques. And we have liquefaction at depth throughout this area. What jumps out in red is this shallow liquefaction directly beneath that end of the building. That shallow stream is not in these locations, but it is over here, and that's why you have the damage there. Not just because of the volumetric settlement, not just because of shear, but also because of ejecta. With that case history, so you start with the observations, and then you fill it in with some CPTs, then we came back and did borings, then we do laboratory testing. So we've had an army of soldiers march through this problem. Then we finally say, okay, Roberto, now we're bold enough with a calibrated model of PM4 sand working within FLAC to do an analysis of this building and see if we can capture the deformation of the south side relative to the north side. Because now we calculate that the north side should have moved, and it did move down, punch down some, the 60 millimeters or so, but the south side settled significantly more. And we pat ourselves on the back that our model does not calculate what was measured. It shouldn't, because my continuum-based model can capture volumetric and shear. It cannot capture ejecta. So if my model matched what was measured, I'd be wrong. Once I estimate how much ejecta came out of the ground and I estimate how much shear-induced deformation, then I get the right answer. Okay? There was no ejecta on the north side, but there was significant ejecta on the south side. So it's important to realize what your model does do and what it can't do. Looking at a few other case histories and also the previous work we've done, we said, you know, now we're bold enough to do a lot of analysis and really see what matters. We trust the model enough to run a sensitivity analysis and look at different thicknesses of liquefiable layer, different thicknesses of the non-liquefiable layer, different relative densities, obviously different widths of a foundation, different contact pressures, different heights, different ground motions. And we run all those different ground motions through this array of different cases to see what's important. And we see that, one, the analysis clearly shows that largely it's shear-induced deformation, not volumetric, that governs building behavior during strong shaking in those cases where ejecta is not significant. Obviously, if the ejecta is significant, that kind of rules the roost. And then it was important that say that certain key ground motion parameters, and so this cumulative absolute velocity and the spectral acceleration at 1 second were the best ways, the optimal ways of characterizing the ground motion, the seismic demand. In terms of site parameters, a number of things are important, but relative density of the liquefiable layer, the thickness of the liquefiable layer, and the thickness of the non-liquefiable crust, because that positions where the liquefiable layer is, were key site parameters. And in terms of building parameters, the building pressure, the contact pressure, and its width were important. And we tended to find, just like you use base heave calculations for excavations, if the factor of safety, static, post-liquefaction factor of safety for bearing capacity was low, you had a problem. You had large deformations. With all that data, and I don't want to go through the details of it, how we start with those case histories, and we do all that field work, we do all that laboratory testing which supports all the analysis with enough confidence in the analytical method, we then run all that sensitivity analysis, and we come up with a way for engineers in a simplified way to get an initial assessment of what the shear-induced settlement will be. I came up with a new parameter that brings in relative density and thickness of the liquefiable layer, because you don't measure relative density directly, so we tie this directly to the cone tip resistance. We bring in the contact pressure, the width of the foundation, these ground motion parameters, and you should not use this until you check it against the case histories. Most of these 19 case histories were not the case histories we used to calibrate the model. Some of them were, but not all. Only after we have these case histories where we sit there and go, I have the detailed plans and the ground conditions for this building. I have the detailed plans for the Christchurch City Hall, Town Hall. I have it for the building C's in Adipazori and for F building in Adipazori. I have ground motions from the Kocaeli earthquake in Turkey. I have ground motions from the Christchurch earthquake in New Zealand, the Darfield earthquake, the June event. I have these case histories where I have good confidence on estimates of the observed shear-induced deformation, and then I can check it against this simplified method, and I find a consistent development, a consistent estimate. So we start with the field case histories, which is because GEER people dropped everything and went out there and captured this perishable data. That started it all. And then after we come up and we're bold enough to make an advanced method or a simplified method actually for estimating settlement, we come back to these well-documented case histories to say, does this make sense or not? Would you as a practicing engineer use this method? Only if it makes sense against the field case histories. So it starts and ends with the field case histories. So in conclusion, turning disaster into knowledge. A well-documented case history, as the geotechnical engineers in the room all understand, that's the key to our profession. That's the cornerstone. That's why we are so much focused on the field, because we want reality, which can't necessarily be replicated in the field or in the computer. And so therefore, having those well-documented case histories are going to allow us to move forward in terms of understanding extreme events and their effects. Reconnaissance is clearly no longer about taking notes and taking your own slide. It's about everything digital and sharing everything. It's about everyone having a UAV and capturing key data that allows them to capture the quantitative data that makes an excellent case history. Everything is geocoded. You will not see a GEER report where an observation is not giving you GPS coordinates. If you can't go back and reoccupy that site because you don't know where it is, you're not going to be able to capture that. In fact, I learned that the hard way when I was flying in the helicopter with Professor O'Rourke. We crossed paths all the time after the Kobe earthquake. I saw surface fault rupture go through a tennis court. I don't know if you slice, but if you sliced, you'd like to play on this course because the right lateral, it allowed you to slice and get your ball in. So I asked the pilot while we were up in the air, I go, do you know where that is? He goes, yes, I know where that is. And so we land on the ground, and I go, where is it? And he goes, it's here. It took me 6 hours on the ground to find that tennis court. When I went to Turkey in 1999, when I flew over an area, I had a GPS, a Garmin 3 Plus. And when I flew over something, I clicked my thing. I knew where I was all the time, and I could send people to sites. Sites I did not physically go on the ground. If I flew over them and I had the GPS coordinates, I could say, go to this location. Remote sensing is powerful in terms of getting your eyes up in space, literally. LiDAR from the air, from the ground. But I think structure for motion is just going to revolutionize the way we capture this post-event conditions. And in the end, I'm still, in terms of revolutions, Google Earth has changed the way we see the Earth. It's changed the way we see the ground and can organize. People can go out, they can get their KMZ files that tell them where they've been, they can put it all together, and I can basically map it on Google Earth, and I can manage the reconnaissance. Thank you very much.
Time for a few questions.
Yes.
Sir, thank you for your lecture. I have one question for the different chart that you printed for the PI less than 12 feet by different potential. Like, how do you define the liquefaction failure in your database? Like, do you observe it in the field? Like, you have to observe the liquefaction?
So the liquefaction started with the field observations because we found sites where we saw clear ejecta or we saw significant building damage and in terms of settlement. So then we went to those sites, we collected samples, we did the CPT, and we said if we ignore the Chinese criteria, all of these things make sense. If we use the Chinese criteria, which is focused on the clay, on the amount of clay size particles, then we can't explain this. So then okay, now that we've done that drilling sampling work in the summer of 2000, then we come back and say, now let's do some careful sampling. Let's bring over the Dames & Moore hydraulic piston sampler, which I think is one of the best sampler devices for clays and silts, and let's sample and do triaxial testing. Let's start off, because these can be non-uniform, so let's get good at being able to see when we have a 6-inch sample that we think is fairly uniform. Let's take Atterberg limits at the top, the middle, the bottom. Let's go ahead and do that in detail. In fact, Rodolfo Sancio, who's a practicing engineer in Houston, was one of the best field laboratory engineers I've ever worked with. And I was lucky enough to have him trained by his father, who's a Ph.D. in geotechnical engineering. His mother's an engineering geologist. He had worked in Venezuela for 4 years as a practicing engineer. He just happened to be at Berkeley. He was going to do shaking table tests. I said, no, you're going to do field tests now. Then we do that careful sampling testing. And then we do testing, and we actually find that my hypothesis was if the soil has a low PI, like PI of 2 to 4, it'll be in one camp. And if the PI is maybe 4 to 8, it'll be in another camp. And then the PI, that was my hypothesis. I was wrong. That there wasn't a significant difference whether the PI was 12, 10, 8. So there appear to be basically non-plastic materials, then there's slightly plastic materials, and then there's highly plastic materials. And we saw the break at a PI of 12. Now, nothing's ever black and white, but that's kind of where, as the soil had a significantly higher PI. So it's that field observations, then it's the careful investigation of the field conditions with the CPT and some sampling, and then it's actually doing very careful undisturbed sampling so you can do the triaxial testing. He did over 110 triaxial tests. He did over a dozen simple shear tests to kind of back that up. And then since then, that criteria has been used in Taiwan. I went back to the Northridge earthquake and showed that, yes, this criteria works for other earthquakes as well. In fact, I almost felt like I was reliving Adapazari, Turkey when I went to Christchurch, because you start with the observations, then you do the CPT work, then you follow that with careful sampling and testing, then you do the advanced analysis, and then you're bold enough to basically make some recommendations that you hopefully think that practicing engineers might listen to.
Other questions?
Yes, Dr. Rathje.
Yeah, great job, John. You know, listening to your talk today, first time it hit me that given all the characterization, careful characterization you've done for these case histories, I'd like to hear your thoughts on how engineers should do site characterization in a forward analysis. How much detail? How do you bring in geology? How much can you do, and how much can you expect an owner to pay?
No, that's, you know, the more time you invest in a site, the more you learn about it. So I think it has to be done on a case-by-case basis. But for example, we initially focused on Christchurch, and I talked today about where there was liquefaction and the damage. But as you know, we've been working now on sites where our methods say there should have been liquefaction and there wasn't. And when we look at that, we see, oh, these are overbank deposits that are highly stratified, that have a little bit of stand. Our methods say low tip resistance all the way down, and even with a fines contact correction, they basically say the whole thing should liquefy. Yet we have field data that says these sites had no surface manifestations of liquefaction. So it's the geology. It's the geology. It's the geology. And so I think it's key to sit there and go, one of the things I've come back to is a couple of things. Is one, continuous sampling. So Christine went back to New Zealand, and I said, we've got to do this because it's just sitting there. We did continuous sampling from about 1/2 meter down to about 7 meters, and she and Sarah, a geologist, pushed every sample out, scored it and broken open, and detailed map all of that. And so her thesis has all that detailed mapping, and then you can see the soil as it is. A cone is wonderful for a homogeneous, thick deposit of medium clean sand, but it doesn't capture the true geology and the true layering that's so critical for the system response of those materials. And so I'm a big believer in reminding myself of what I learned early on working with Jerry Lenders on a failure back at Purdue. is continuous sampling and geologic mapping. And I've used that a couple times in my career, and I've always been glad I've done that because I can gain that. Can I put a number on that? Not exactly. We're trying to work toward that. But it does affect reality, and it should affect my engineering judgment. So I think that depositional process is so critical. The other thing besides continuous sampling is scanning electron microscopes to look at the soil. I mean, you like to look at a sand and you can look at a gravel, but why not look at the soil? Some soil in Treasure Island off the coast, off of Yerba Buena Island in San Francisco, NGO was basically trying to do ground improvement. And the cone basically said it was all the same. They did significant testing of vibration, and they found the loose, clean fill on top all densified, and they got good response. And the tip resistance went way up. But in the native material, which had the same tip resistances, didn't change. In fact, in one location, it got worse. And I said, you know what, this is the time for continuous sampling. Once we saw that, we saw there were little bugs had gone through there and deposited whatever they deposit. And it was a layered medium. It was a shoal that had this active movement back and forth. The cone was misleading. And unless you have a geologist and a geotechnical engineer doing careful investigation of the actual layering of the soil, you're never going to get that.
Any other questions?
Yes.
Yes, sir.
So you have presented, I guess, recent advanced equations on calculating the sediment.
Yes.
Has there been any recent equations or apps?
Actually, Professor Mieszko Czubnowski is coming up with something. So my work has come out in the soil dynamics and earthquake engineering. So you can go to that and use that today. His work, he has a very fine paper that he published in the Vancouver conference, that performance-based design 3, which was in July of this year. That is the start of it. And you guess what? A lot of it's geology, because there's certain geologic depositions that lead for a layer that basically is a thick layer of sand that builds up water under an impermeable layer that basically has the thing slide on it. And there's other ground that doesn't have that geology. It doesn't have the lateral thing. So it's not just doing cones, but he's going to bring in a key element of geology to be able to classify these lateral spreads. It's still qualitative, but I expect, knowing Professor Czubnowski, you'll see something more quantitative come out of that. And I think you've done some stuff on lateral spreading as well. Is that ready for prime time?
I think there's a lot of people that are working on lateral spreading from the Christchurch earthquake. It's an amazing data set in terms of having really high-quality lateral displacements and various types of remote sensing techniques. We're finding a lot of the empirical models are having some, or semi-empirical models are having some issues. So I think Mieszko, as well as ourselves, are looking more towards using the advanced numerical methods to favor certain issues.
Follow-up question is, in terms of numerical analysis, you show PM4 as an all zero. Is that a latest and greatest?
Okay, depends on whose model it is. Professor Boulanger convinced me it was the latest and greatest. And I know, and I've used many models. I've gone all the way from modified Cam Clay, Duncan hyperbolic, to using Lade's model, to using UBC sand, different versions of it, to PM4 sand. I like PM4 sand because it's strong mechanistic underpinning. It's based on Defias and Masseri. And Professor Boulanger is a phenomenal engineer, and he tests it in every possible way. But it's one of the many models. One of the things that I did, though, is I realized, you know what? I don't want my method just to be based on flak with PM4 sand, because as well as I've calibrated it, and I think it works really well and provides good insight, it can't be the truth. Dr. Dashti at University of Colorado Boulder was kind enough to say, you know what, I'll share the results of my data. So they just finished a thesis, and she had run OpenSea's three-dimensional analysis with Elgamal's model, the pressure-dependent model. And so she just gave me, I said, I don't want to see the details, just give me the results. These inputs, you got these results. And we both back analyzed the same set of centrifuge tests, and our results are almost on top of each other. In fact, that's in the paper published in Soil Dynamics and Earthquake Engineering. So when two different people working separately at least agree, there's a pretty good chance that they're both not wrong.
More questions? Everybody's happy? Good. Well, John, I want to thank you for a fantastic lecture. What struck me also is your passion for this topic. So we really appreciate this. Here's the check.
Thank you.
And the plaque that reads, Texas A&M University Zachary Department of Civil Engineering recognizes Professor Jonathan Bray for presenting the 25th Buchanan Lecture entitled Turning Disaster into Knowledge, 13 October 2017, College Station, Texas. The lecture was established in 1993 in recognition of Professor Spencer J. Buchanan.